America is racing to finish some of its biggest engineering projects in 2026. From massive bridges to towering urban developments, these mega projects are reshaping the nation at an astonishing scale. In this video, we explore the American engineering giants nearing completion and reveal how they could transform the transportation industry and the future of the country's infrastructure. At John F. Kennedy International Airport, one of the most important US megaproject milestones in 2026 is the opening phase of the new Terminal 1, a major redevelopment on the airport's south side in New York. This project is designed to replace the former Terminal 1, Terminal 2, and the site of the former Terminal 3 with a single, much larger international gateway. It is one of the central pieces of JFK's broader airport transformation, and in 2026, the focus is on turning a long-running construction site into an operating terminal environment. The new Terminal 1 is planned as a large-scale international terminal with modern aircraft gates, expanded passenger processing space, upgraded baggage systems, new security screening areas, and infrastructure designed for wide-body aircraft used on long-haul routes. Its importance comes from both scale and function. JFK is one of the main international entry points into the United States, and the terminal is being built to increase capacity, improve circulation, and support a more efficient border, customs, and airline operation than the older facilities it replaces. Construction work leading into 2026 is centered on delivering the first completed section of the terminal. That includes finishing the structural frame and enclosure of the initial concourses, completing interior fit-out, installing mechanical, electrical, and plumbing systems, testing baggage handling equipment, commissioning airfield side systems, and preparing passenger processing zones for operation. Road access, curbside works, utility connections, and apron infrastructure also need to be completed in sequence, so the first phase can function as a live airport terminal rather than just a finished building shell. A major challenge is that this work is being carried out inside one of the busiest aviation environments in the country. Construction has to be staged around active aircraft movements, existing terminal operations, security restrictions, and strict commissioning requirements. That makes 2026 especially important because the project must shift from heavy civil and structural work into testing, certification, operational readiness, and phased turnover. In airport mega projects, that transition is often the most difficult part, since systems integration matters as much as the building itself. For a video about US mega projects completing in 2026, the new Terminal 1 fits best as a project reaching a major completion milestone in that year, rather than its absolute final build-out. The first operating phase is expected in 2026, while the full terminal program continues beyond that initial opening through later phases. That means 2026 is the year when the project begins delivering real passenger capacity, even though additional gates, support areas, and final expansion elements may continue afterward. Beneath some of the most congested streets in Los Angeles, the LA Metro D-Line extension, Section 1, is the underground transit project intended to deliver one of the city's most important rail expansions of the mid-2020s. For a video about United States mega projects completing in 2026, this segment matters because it represents the final stage of transforming years of tunneling and station construction into an operating subway link. Section 1 extends the D-Line west from its former terminus at Wilshire/Weston to new stations at Wilshire/La Brea, Wilshire/Fairfax, and Wilshire/La Cienega. This first section is the opening piece of a much larger corridor expansion designed to push heavy rail farther through the Wilshire Corridor, one of the densest employment and destination corridors in Southern California. Its value is not only in adding track mileage, it creates new direct subway access to major cultural, commercial, and residential districts while reducing dependence on slow surface traffic along Wilshire Boulevard. That makes Section 1 a foundational part of a broader network change rather than a standalone line. The most significant construction already involved tunnel boring, cross passages, station excavation, concrete structural work, and the build-out of underground platforms and circulation areas. By the final approach to completion, the work shifts away from excavation and toward railway systems and passenger facilities. In a 2026 completion context, the critical construction activities are the finishing of station interiors, installation and testing of elevators and escalators, completion of ventilation and fire life safety systems, traction power energization, track and third rail finishing, signal integration, communication systems, fare equipment, and the final architectural treatment of entrances and public-facing spaces. Another major task in the completion phase is systems commissioning. For a subway extension, the project is not complete when the tunnels and stations are physically built. Metro and contractors must test train control systems, verify emergency procedures, integrate power and communications, certify ventilation performance, and run trial operations before passenger service begins. That period is often one of the most demanding parts of the schedule because the project has to function as a fully coordinated transport system, not just as a completed civil structure. Section 1 also has to be understood within the timeline of the larger D-Line extension program. It is the first of 3 major sections, meaning its completion has operational importance beyond its own stations. Once open, it becomes the base from which the later western sections connect toward Beverly Hills, Century City, Westwood, and eventually the VA campus. That makes Section 1 the first visible delivery of a longer strategic investment that has been advancing in phases. In Northern California, the BART Silicon Valley. Phase 2 project is one of the largest transit expansions associated with the next stage of US infrastructure delivery. But for a video about United States megaprojects completing in 2026, it has to be described carefully because this project is better understood as a major construction program, advancing toward later delivery milestones rather than a simple single-year completion story. Its purpose is to extend Bay Area rapid transit from the Berryessa/North San Jose area farther into Santa Clara County through downtown San Jose and on to Santa Clara, creating the long-planned rail connection between the regional BART network and the core of Silicon Valley. The project is significant because it is not just a surface rail extension. It is built around a complex urban alignment that includes substantial tunneling, underground station construction, systems integration, and interface work in one of the most constrained and economically important urban corridors in the United States. The extension is planned to add several new stations, including underground stops in central San Jose, and it is intended to connect major employment districts, regional transit facilities, and dense urban destinations that have historically lacked direct BART service. For a 2026 focused mega project segment, the relevant point is the construction work being done in 2026 to move the program toward its final outcome. That work is expected to center on major civil construction, utility relocation, excavation support, station box development, tunnel-related preparation or advancement, structural concrete operations, systems facility construction, and the continuing build-out of rail infrastructure elements needed for later operating service. On a project of this scale, 2026 is the kind of year in which visible progress comes from heavy engineering execution rather than ceremonial opening. Contractors and agencies would be focused on sequencing underground works, maintaining traffic and utility service above active construction zones, and preparing the corridor for the later installation of track, power, ventilation, communications, and life safety systems. Across the Northeast Corridor, the Gateway program's Hudson River tunnel component is one of the most consequential transportation megaprojects in the United States. But in a 2026 focused video, it should be framed as a project reaching critical construction acceleration rather than full end-of-project completion. Its purpose is to build new passenger rail tunnels under the Hudson River between New Jersey and Manhattan, and then allow the existing century-old tunnels, which were heavily damaged by saltwater intrusion during Hurricane Sandy, to be rehabilitated without cutting the region's rail capacity in half. That is why the project is treated as a national infrastructure priority rather than a local rail upgrade. The core problem is capacity and reliability. The existing 2-track tunnel is a bottleneck for intercity and commuter rail traffic entering Penn Station. It carries Amtrak and NJ Transit trains on the busiest passenger rail segment in the country, yet it lacks redundancy. Any major service disruption affects travel across the Northeast. The new tunnel project is intended to solve that by adding parallel tunnel capacity first, creating the conditions for later rehabilitation of the old tubes while maintaining service. The important point is that 2026 is associated with major active construction and package-level milestones, not with the final opening of the full tunnel system to passengers. In that year, the key work is expected to include continued heavy civil construction on approach structures, tunnel portal, areas, retaining structures, utility relocation, ground improvement, excavation support, concrete works, and early tunnel-related infrastructure on both sides of the river. Where contracts are advanced enough, 2026 activity also includes site preparation for full tunneling operations, staging areas, access shafts, and the supporting infrastructure needed before boring or immersed structural progress can translate into final rail systems installation. The project is unusually complex because it is not only a tunnel beneath a major river. It has to connect into one of the most constrained rail environments in North America. On the Manhattan side, work must interface with Penn Station approaches, densely developed urban blocks, utilities, transportation corridors, and existing rail operations. On the New Jersey side, the alignment must tie into the broader network while managing wetlands, embankments, and active right-of-way conditions. Every phase depends on sequencing, civil, structures, ventilation and safety provisions, drainage, trackbed preparation, and future system spaces all have to be coordinated long before trains can operate. Another major issue for the 2026 timeline is that the Gateway program is not a single construction contract. It is a portfolio of interdependent elements, including tunnels, portal works, bridge-related interfaces, and supporting rail infrastructure. Because of that, completion can mean different things depending on the contract package being discussed. Some enabling components may reach major completion earlier, but the overall Hudson River tunnel element remains part of a longer delivery schedule extending beyond 2026. Off the coast of Virginia, the Coastal Virginia Offshore Wind Project is scheduled to reach its defining construction phase in 2026, when the offshore installation campaign and grid connection work are expected to push the development from a marine works program into an operating energy asset. This is one of the largest energy megaprojects advancing toward completion in the United States, built to establish a commercial-scale offshore wind facility in federal waters east of Virginia Beach and to deliver a major new source of electricity into the regional grid. The project consists of a large field of offshore wind turbines, subsea cable systems, offshore substations, onshore transmission connections, and the related port and logistics infrastructure needed to assemble, transport, and install heavy components at sea. Its scale makes it different from earlier US offshore wind efforts. This is not a pilot installation or a small demonstration array. It is a utility-scale generation project intended to add substantial capacity through a coordinated marine construction effort involving specialized vessels, fabrication supply chains, and grid integration works on land. The most important construction activity associated with completion in 2026 is the offshore erection sequence. By that stage, work is focused on installing turbine foundations, transition pieces, towers, nacelles, and blades, along with completing offshore substations and laying or finishing inter-array and export cables. Each of these activities depends on weather windows, vessel availability, marine coordination, and strict sequencing. Foundation and cable work must be sufficiently advanced before final turbine installation can move efficiently, and energization cannot occur until both offshore and onshore systems are ready for integrated testing. Onshore construction in 2026 is also essential to completion. That includes cable landfall works, underground or corridor-based transmission connections, substation completion, electrical equipment installation, control systems integration, and final commissioning preparations. For a project of this kind, completion is not defined only by the last turbine standing offshore. It depends on the point when generation equipment, transmission, infrastructure, protection systems, and grid connection assets are all tested together and accepted for service. In Central Ohio, the Intel Ohio Semiconductor Campus, Phase 1, is one of the most closely watched industrial megaprojects tied to the United States manufacturing build-out in the second half of the decade. It is designed as the first stage of a large semiconductor production complex near Columbus, with Phase 1 centered on 2 leading-edge chip fabrication plants and the extensive support infrastructure required to operate them. In any 2026 completion discussion, this project has to be described as a major construction and delivery milestone rather than a simple fully finished campus, because semiconductor facilities are completed through overlapping stages of shell construction, utility activation, clean room installation, equipment move-in, and production ramp. Phase 1 is significant because a semiconductor fab is not only a large building, it is a highly controlled industrial system made up of clean rooms, vibration-managed foundations, chemical delivery networks, water treatment systems, power distribution equipment, air handling systems, process piping, backup systems, and security-controlled production space. The visible structures are only one part of the build. Much of the project's complexity is in the hidden technical infrastructure that allows fabrication tools to operate within extremely strict environmental tolerances. The construction work associated with reaching key 2026 milestones is concentrated on finishing the main fab structures, closing the building envelope, completing mechanical and electrical plant systems, and pushing the site from heavy civil work into interior technical fit-out. By that stage, work includes structural steel and concrete completion, where still ongoing utility corridor development, substation and power infrastructure advancement, installation of water and wastewater systems, process piping, HVAC systems, clean room framing, raised floor systems, filtration equipment, and the commissioning of support buildings that serve the fabs. Exterior works also remain important, including internal roads, drainage, logistics areas, and the site-wide infrastructure needed for a campus that is expected to expand in later phases. A critical distinction for semiconductor projects is the difference between construction completion and operational readiness. Even if major building work reaches an advanced state in 2026, that does not automatically mean full chip production begins immediately. After the physical facilities are largely complete, there is usually a long sequence of cleanroom certification, systems balancing, contamination control verification, specialty equipment installation, tool hookup, process testing, and early production qualification. That means 2026 is best understood as a year of major physical completion and systems transition for Phase 1, with final industrial readiness depending on how quickly the project moves through commissioning and tool installation. Rising on the south shore of Lady Bird Lake, Waterline Tower is one of the most prominent high-rise construction projects associated with Austin's late 2020s development cycle, and in a 2026 context, it stands out as a project moving through the final stages required to convert a super tall structure into an occupied mixed-use building. The development combines residential, hotel, office, retail, and parking functions in a single vertical complex, making it more than a conventional apartment tower or office building. Its significance comes from both height and program density. It is designed to concentrate several major urban uses into one structure at a key downtown site, directly tied to the growth of Austin's skyline and central business district. The project's construction profile is defined by the demands of a very tall, reinforced concrete and steel high-rise built in a constrained urban environment. Earlier phases focus on excavation, foundation work, podium construction, vertical structural progression, floor plate formation, and the coordination of elevators, mechanical risers, and core systems. By the time a project like this enters the 2026 completion window, the central task is no longer simply adding height. The emphasis shifts to enclosure, systems activation, interior build-out, facade completion, and the commissioning work needed for each separate use within the tower. For a project approaching completion in 2026, the most important construction activities during that year would include finishing the curtain wall and exterior skin, completing waterproofing and roof assemblies, finalizing elevator installation and testing, and continuing the mechanical, electrical, plumbing, and fire life safety fit-out across the tower. Interior work becomes the dominant effort. Residential levels require unit completion, corridor finishes, life safety certification, and amenity installation. Hotel floors require guest room build-out, back-of-house systems, kitchens, service circulation, and hospitality-specific commissioning. Office components require lobby completion, vertical transportation readiness, tenant infrastructure, and the handover conditions needed for interior occupancy or later tenant improvements. Ground-level retail areas also move toward storefront completion, utility connection, and public access readiness. Another defining feature of a mixed-use tower like Waterline is that completion does not occur as one simple moment. Different parts of the building can move toward turnover on different sequences. Parking and base building systems may be ready before hotel interiors. Residential units can complete in batches. Retail shells may be delivered before tenant-specific fit-outs. Because of that, 2026 should be understood as the year of final construction execution and phased readiness rather than a single identical completion milestone for every component. In practice, this means the project's schedule is shaped by inspections, testing, punch list correction, systems balancing, facade closeout, and occupancy approvals as much as by visible structural work. Set within Exposition Park in Los Angeles, the Lucas Museum of Narrative Art is one of the most distinctive cultural construction projects advancing toward completion in the United States in 2026. The project is designed as a major museum dedicated to narrative art in multiple forms, including illustration, painting, photography, comics, cinema-related material, and digital media, with a building program that also includes galleries, theaters, educational space, archives, public landscape, and visitor facilities. Its significance in the 2026 construction cycle comes from the fact that it is not a standard institutional building. It combines complex architecture, specialized museum systems, and extensive site integration in one of Los Angeles' most important civic districts. The structure itself is central to the project's identity. Unlike a conventional rectangular museum, the building is defined by a sculptural form with a continuous exterior envelope and a highly controlled interior environment. That architectural approach creates additional complexity in both construction and completion. The work is not limited to erecting floor plates and closing a facade. It requires precise coordination between structural systems, exterior cladding, waterproofing, environmental controls, and the interior gallery conditions needed for long-term preservation of artworks and archival materials. By the time the project reaches its 2026 completion phase, the most important work is concentrated on final enclosure, systems commissioning, interior fit-out, and landscape integration. Exterior construction in that period includes completion of the outer skin, sealing of the building envelope, roof finishing, drainage resolution, and the final detailing, required to protect the structure and create stable internal environmental performance. Inside the museum, the key construction activities include gallery finishing, installation of climate control systems, lighting systems, fire protection, security infrastructure, vertical transportation, theater and presentation spaces, back-of-house support areas, and the specialized mechanical and electrical systems required for museum operations. A museum of this type also depends on exact environmental calibration before it can function. Completion is not achieved when the building is visually finished. The project has to move through balancing and testing of temperature, and humidity controls, life safety certification, access control integration, audio-visual commissioning, and the preparation of collection handling spaces. Exhibition areas require carefully controlled lighting and air management. Storage and archive areas need stricter performance standards than many ordinary public buildings. That makes the final year of construction particularly technical because the project is transitioning from architectural completion into operational readiness. North of Phoenix, the TSMC Arizona Semiconductor Fab project is one of the most important industrial construction programs tied to United States megaproject delivery in 2026. But it has to be described in phases because the site includes multiple fabrication plants and supporting facilities with different completion and production timelines. The Arizona development is designed as a high-end semiconductor manufacturing campus with fabrication buildings, utility plants, clean room space, water systems, power infrastructure, chemical handling systems, administrative areas, and logistics support all built as one integrated production environment rather than as isolated factory shells. Its importance comes from the nature of semiconductor manufacturing. A fab is not complete when the structure is topped out. The visible building is only the outer layer of a much more complex technical system. Below and inside the shell are vibration-sensitive slabs, redundant power feeds, process cooling, ultra-pure water generation, wastewater treatment, specialty gas delivery, chemical distribution, air filtration, and clean room infrastructure that must operate to extremely tight tolerances. That means the final construction stages in 2026 are driven less by general building work and more by technical fit-out, systems integration, and equipment readiness. For a 2026 megaproject completion discussion, the Arizona Fab site is best understood as reaching major completion milestones during that year, rather than finishing every long-term phase of the campus at once. The key construction activities in 2026 are likely centered on interior cleanroom completion, mechanical and electrical plant finalization, process utility installation, hookup of manufacturing support systems, and the transition from base building, construction into tool installation and commissioning. Work at that stage typically includes completion of air handling units, duct systems, chilled water and condenser systems, chemical piping, specialty gas cabinets, exhaust systems, clean room ceilings, raised access floors where required, control systems, fire life safety integration, and final testing of building performance. Another defining issue is the distinction between construction completion and production start. Once the fab building and support systems are finished, the project still has to move through cleanroom certification, contamination control verification, installation of lithography and process tools, utility hookups to each tool, calibration, pilot runs, and yield qualification. Because of that sequence, 2026 should be treated as a year in which construction is completing the conditions for operations, even if the manufacturing ramp continues beyond the point at which the buildings themselves appear finished. Linking hydropower from Canada directly into New York, the Champlain Hudson Power Express is one of the most consequential transmission mega projects moving toward completion in the United States in 2026. The project is a long-distance, high-voltage direct current line designed to carry electricity from Quebec into New York City through a predominantly buried and underwater route. Its importance comes from both function and route strategy. Instead of relying mainly on new overhead corridors, the line is built largely beneath Lake Champlain, the Hudson River, and selected land segments, reducing surface disruption while creating a major new clean power connection into one of the country's largest electricity markets. The project consists of transmission cables, converter station infrastructure, landfall construction, buried terrestrial segments, underwater, installation works, interconnection facilities, and the control systems needed to operate an HVDC link across a long and technically varied corridor. Unlike a conventional generation project, this is an energy delivery mega project. Its value depends on whether the line can be physically installed, electrically integrated, and commissioned as a complete corridor. That makes the final construction period in 2026 especially important because the system only becomes useful when the entire route and terminal equipment are ready together. The key construction work associated with 2026 completion is concentrated on the final cable installation segments, jointing and burial work, shoreline and transition point completion, and the finishing and energization of converter facilities. For a project using long submarine and underground cable runs, completion is not simply a matter of laying cable. Crews also have to complete trenching where required, backfill and protection measures, splice, vault work, cable testing, restoration of disturbed land segments, and the final interface between marine installed and land-based sections. Converter station work is equally critical, including installation of power electronics, transformers, cooling systems, protection equipment, control systems, and grid interconnection infrastructure. The schedule significance of 2026 is tied to the project's shift from corridor construction to electrical readiness. Earlier phases are dominated by permitting, manufacturing, route preparation, marine logistics, and initial installation campaigns. By the final approach to service, the project enters a more technical stage defined by testing and commissioning. High voltage direct current transmission requires extensive verification before operation. Insulation integrity, converter performance, communications, protection schemes, and system synchronization all have to be proven before the line can enter commercial service. That means the decisive work in 2026 includes not only physical construction, but also the final electrical and operational validation of the entire connection. The Pacheco Pass segment falls within the broader Merced to San Jose section, which is in the advanced pre-construction phase. Full-scale construction is expected to begin in late 2026 or early 2027, following the completion of design, environmental permitting, and contractor procurement. In 2026, geotechnical investigations are being conducted at multiple points across the alignment, including test drilling to analyze subsurface conditions, fault mapping near the Calaveras and San Andreas fault zones, and seismic risk assessments required for final tunnel engineering. The tunnel alignment will require two main bores with an internal diameter of approximately 40 feet each, separated by cross passages every 1,000 to 1,500 feet to allow emergency access and pressure equalization. An intermediate access shaft is also planned in the vicinity of Casa de Fruta to provide tunnel boring machine launch capability and logistical support during construction. The geology of the Diablo Range presents significant challenges with faulted rock zones, variable water inflows, and compressible soils in valley transitions. Tunneling will be conducted using pressurized tunnel boring machines capable of navigating mixed face and high pressure conditions. The Pacheco Pass tunnels will pass under critical infrastructure, protected habitat areas, and seismic fault lines, requiring advanced lining systems and continuous monitoring. Designs include seismic isolation joints and drainage galleries to mitigate fault displacement risk and groundwater intrusion. Tunnel depth will range from 100 to over 1,000 feet below surface, depending on terrain. Ventilation and safety systems, including emergency egress, fire protection, and pressurization controls, are part of the ongoing systems design effort in 2026. Upon completion, the tunnels will enable a seamless high-speed rail corridor from Merced to Gilroy, reducing rail travel time across the pass from over an hour to just under 15 minutes. Combined with viaducts, embankments, and cut and fill sections across the San Joaquin Valley and into the Santa Clara Valley, the Pacheco Pass alignment represents one of the most capital-intensive and engineering-heavy components of the entire HSR system. The full Merced to San Jose segment is targeted for phased operational readiness beginning in the early 2030s, contingent on funding and right-of-way clearance. In 2026, contract packaging and procurement strategy are being finalized. The tunnel construction will likely be delivered as part of a design-build package, integrating civil structures, systems, and tunnel fit-out under a single delivery framework. Coordination with Caltrain and Union Pacific Railroad in the Gilroy area is also active in 2026. where blended operations with existing rail infrastructure are being planned. At full build-out, the Pacheco Pass tunnels will serve as the gateway between the Central Valley's agricultural and inland urban centers and the tech-driven economy of Northern California. The tunnels are expected to handle multiple high-speed rail trains per hour in each direction, forming a high-capacity backbone for statewide intercity travel. Their construction, once launched, will take an estimated 6 to 7 years, involving around-the-clock excavation and a continuous logistics chain to manage spoil removal, liner segment installation, and tunnel utility integration. South of Chicago's Loop and directly east of Grant Park, one of the most ambitious and complex megaprojects ever proposed in the city is planned not on open land, but above active rail infrastructure. One Central Chicago is a large-scale, long-term development proposal centered on constructing a massive transit-oriented platform over the Metra Electric Rail Yard near Soldier Field, redefining how Chicago approaches air rights development. The core of the One Central proposal is the construction of a multi-level structural deck spanning more than 30 acres of rail lines. This deck would serve as the foundation for an entirely new neighborhood, allowing vertical development to rise above existing transportation corridors without displacing them. The engineering challenge is central to the project, requiring heavy load-bearing caissons, vibration isolation systems, and phased construction that allows uninterrupted rail operations below. The project is structured around a new central transit hub, envisioned as one of the largest in the Midwest. The hub would integrate Metra electric trains, CTA bus services, potential future rail connections, and pedestrian and bicycle networks into a single, consolidated station. Transit infrastructure is planned as the first major construction phase, establishing the structural deck and station facilities before any private buildings rise above. One Central is approved conceptually as a multi-decade development, not a single construction effort. The full build-out is projected to extend into the 2040s, with individual phases dependent on financing, tenant demand, and infrastructure funding. Early construction would focus on the deck, transit facilities, and utility systems, a process expected to take several years before vertical development begins. The proposed scale places One Central among the largest megaprojects in Chicago history. At full build-out, the plan allows for millions of square feet of mixed-use development, including residential towers, office space, hotels, academic and research facilities, and cultural venues. Building heights would vary across phases, with some towers reaching high-rise and super tall classifications, though final designs remain flexible. Infrastructure construction is the defining feature of the project. Beyond the deck itself, One Central requires new roadways, stormwater management systems, electrical substations, and telecommunications networks. Because the site sits between Lake Michigan and downtown, flood resilience and drainage engineering are critical components of the design. Elevated building pads and integrated water management systems are planned to address long-term climate risks. Unlike many Chicago megaprojects, One Central has not yet entered full construction. As of the mid-2020s, the project remains in advanced planning and approval stages, with negotiations focused on public-private partnerships, transit funding, and long-term governance. The project's viability is closely tied to securing funding for the transit hub, which is considered essential to unlocking the value of the surrounding development. The location gives the project strategic importance. It sits between the museum campus, McCormick Place, Soldier Field, and downtown, creating a potential bridge between Chicago's civic core and its convention and entertainment districts. The development would also reconnect neighborhoods long separated by rail infrastructure, using the deck as both a building platform and a public realm. From a construction sequencing standpoint, One Central differs from traditional real estate projects. No single building can proceed independently. Each phase depends on completion of shared structural and transit elements, making coordination and long-term scheduling central to the project's execution. This complexity places One Central closer to infrastructure megaprojects like transit expansions than conventional mixed-use developments. Long before Miami's skyline signaled its rise as a global city, the expansion of Port Miami and its tunnel interchanges quietly re-engineered the region's economic foundation through one of the most consequential infrastructure megaprojects in the county's history. Port Miami, located on Dodge Island in Biscayne Bay, underwent a coordinated expansion program during the late 2000s and early 2010s, aimed at transforming the port into a post-Panamax global trade hub. This effort combined portside construction, navigational improvements, and highway-grade tunnel interchanges into a single integrated mega-project. The goal was to remove physical, maritime, and logistical constraints that limited cargo growth while separating freight movement from downtown Miami's surface streets. One of the earliest and most critical construction components was the deepening of the port's main navigation channel. Prior to expansion, the channel depth restricted access for larger container vessels. Dredging operations began in the early 2010s and involved removing millions of cubic yards of material from Biscayne Bay to achieve a depth of approximately 50 to 52 feet. This work was completed in 2015, timed to coincide with the expanded Panama Canal, allowing Port Miami to receive fully loaded post-Panamax container ships for the first time. On NAS, Dodge Island itself, extensive terminal reconstruction took place in parallel with dredging. Older cargo berths were demolished and rebuilt with reinforced concrete wharves capable of supporting heavier cranes and higher container loads. New gantry cranes, some of the largest in the world at the time of installation, were erected on reinforced rail systems embedded into the key structure. Yard areas were regraded and paved to accommodate automated container handling equipment and higher stacking densities. Utility infrastructure beneath the port was also rebuilt. This included new electrical substations, stormwater drainage systems, fuel distribution lines, and communications networks designed to support modern terminal operations. These upgrades were completed incrementally to avoid disrupting ongoing cargo and cruise activity, requiring phased construction zones across the island. The landside component of the expansion centered on the Port of Miami Tunnel and its highway interchanges, which together form the port's primary freight access system. Construction of the tunnel began in 2010 and was coordinated directly with port expansion schedules. The tunnel consists of two submerged roadway tubes connecting Dodge Island to Watson Island, bypassing downtown Miami entirely. Equally significant were the tunnel interchanges themselves. On the mainland side, major roadway reconstruction was required to tie the tunnel directly into Interstate 395 and Interstate 95. This involved building new elevated ramps, retaining walls, and transition structures capable of handling heavy truck volumes at highway speeds. Existing roadways were demolished and realigned, with traffic maintained throughout construction using temporary detours and phased lane shifts. On the port side, Dodge Island underwent extensive reconfiguration to integrate tunnel portals with internal port circulation. New access roads were built, grade separations installed, and security checkpoints relocated to streamline truck movement. These changes allowed cargo vehicles to enter and exit the port without crossing cruise passenger traffic, significantly improving operational efficiency and safety. The tunnel excavation itself was completed in 2013, but the interchange construction and systems integration extended into 2014. The full tunnel and interchange system opened to traffic in August 2014, marking a major milestone in the port expansion timeline. From that point forward, thousands of trucks per day, were rerouted away from downtown Miami streets and directly onto the interstate network. The expansion program also included rail infrastructure improvements. Port Miami's on-dock rail connection was rehabilitated and reactivated, linking the port directly to Florida East Coast railway lines. Track upgrades, switching yards, and loading areas were constructed to enable intermodal freight transfer, reducing dependence on trucking for long-haul cargo movement. In the context of Miami's biggest megaprojects, the Port Miami expansion and tunnel interchanges differ from high-rise developments by operating as a systems-level transformation. The project did not create a single landmark structure, but instead rebuilt the physical processes that allow the city to function as a logistics hub. Its completion aligned with other regional megaprojects, including airport cargo expansion and downtown redevelopment, forming an interconnected infrastructure network. North of Dallas, in one of the fastest-growing urban corridors in Texas, the Fields Entertainment District in Frisco is emerging as a large-scale, mixed-use mega-project that is actively under construction in 2026. The development is positioned within the broader Fields master-planned community, a multi-thousand-acre site designed to accommodate long-term population growth, corporate expansion, and regional tourism demand. The Fields Entertainment District is planned as a dense concentration of sports, hospitality, retail, dining, and public space, anchored by major destination users rather than traditional suburban commercial formats. Unlike single-purpose developments, the district is structured to operate continuously, supporting large events, daily foot traffic, and future transit-oriented growth. Its scale and phasing place it among the most consequential Dallas area megaprojects progressing through construction in 2026. By 2026, horizontal infrastructure work is largely complete, allowing vertical construction to dominate activity across the district. Roadways, utility corridors, stormwater systems, and site grading were established in earlier phases, enabling simultaneous construction of multiple buildings. In 2026, cranes, concrete crews, and steel framing operations are active across entertainment venues, hotels, parking structures, and retail blocks. One of the primary construction focuses in 2026 is vertical development of large-format entertainment and event buildings. These structures require long-span steel framing, high-capacity foundations, and extensive back-of-house infrastructure. Construction includes structural steel erection, roof decking, and exterior enclosure systems designed to accommodate high occupant loads and advanced audiovisual systems. These buildings are engineered to support concerts, live events, and large public gatherings. Hospitality construction accelerates during 2026. Multiple hotel components within the district are rising simultaneously, with reinforced concrete and steel structures progressing floor by floor. Interior build-outs begin on lower levels as upper floors continue structural work. Mechanical and plumbing systems are sized for high turnover and large conference or event-driven occupancy patterns, reflecting the district's destination-oriented role. Retail and dining blocks are also under active construction in 2026. These buildings are designed with flexible floor plates to allow tenant customization while maintaining consistent architectural standards across the district. Construction includes storefront framing, exterior finishes, service corridors, and shared utility infrastructure. Emphasis is placed on pedestrian connectivity with covered walkways, plazas, and integrated outdoor seating areas built alongside vertical elements. Parking infrastructure represents a significant portion of 2026 construction activity. Multi-level parking garages are being built to serve entertainment venues, hotels, and retail uses. These structures require rapid cycle concrete construction and are designed with future adaptability in mind, allowing potential conversion or integration with autonomous or shared mobility systems later in the project's life cycle. Public realm construction expands significantly in 2026. Central gathering spaces, landscape plazas, and pedestrian spines are being formed as adjacent buildings reach enclosure stages. Hardscape installation, lighting systems, wayfinding infrastructure, and drainage features are constructed concurrently to ensure these spaces are operational as individual components of the district open. These areas are engineered to manage large crowd movements during peak events. Utility and systems integration is a major technical focus in 2026. Electrical substations, district-wide communications networks, and centralized security systems are being installed to support high-demand uses. Fiber networks are integrated throughout the district to support digital signage, ticketing systems, and event broadcasting. These systems are coordinated across multiple buildings to function as a unified operational environment. Well before the first match of the 2026 FIFA World Cup is played in North Texas, downtown Dallas is undergoing a coordinated series of infrastructure and venue upgrades that collectively form one of the region's most complex megaproject efforts active during 2026. Rather than a single construction site, the World Cup preparations consist of multiple overlapping projects focused on transportation, public space, security, mobility, and event operations, many of which reach peak construction or final delivery during 2026.
Jordan Downs wasn't built to last, but it lasted. What began in the 1940s as temporary war worker housing in the heart of Watts evolved into one of Los Angeles's most recognized public housing projects. For decades, it stood as a symbol of neglect, of disinvestment, of the city's fractured promises. Now it's at the center of one of the largest and most complex urban redevelopments ever attempted in Southern California. This is the Jordan Downs redevelopment, a multi-phase billion-dollar megaproject that's rebuilding an entire neighborhood from the ground up. We're not talking about a simple renovation. This is full-scale urban reconstruction, replacing over 700 aging public housing units with a mixed-income community of more than 1,400 new homes, complete with parks, retail corridors, a new street grid, and state-of-the-art infrastructure. And all of it is happening while people still live there. That reality, redeveloping a live-in community without displacement, is what makes this project such a massive logistical and engineering challenge. Everything had to be phased. Crews couldn't just level the site and start fresh. Instead, new housing blocks were constructed in stages on available land, allowing families to relocate within the community as old units came down. That required intense coordination, not just in construction, but in utilities, access roads, and safety systems, all while keeping the neighborhood functioning. Before any new buildings could rise, the land itself had to be re-engineered. Jordan Downs sits on a former industrial site, contaminated from decades of adjacent manufacturing. That meant full environmental remediation, soil testing, removal of hazardous material, groundwater management, and installation of protective barriers. Engineers excavated tens of thousands of cubic yards of earth, replacing contaminated soil with engineered fill, compacted and monitored for stability. Next came infrastructure. The original Jordan Downs layout was a relic of mid-century planning. Isolated blocks with limited connectivity and almost no integration into the surrounding street grid. To fix that, the project involved installing an entirely new road network, complete with sidewalks, bike lanes, storm drains, and underground utilities. A major extension of Century Boulevard now runs through the site, connecting it to the broader Watts area and giving the community a direct arterial link to the rest of the city. Structurally, The new buildings are designed for both density and resilience. Wood frame over concrete podiums dominate the design, balancing cost efficiency with seismic durability. Each structure is engineered with fire suppression systems, earthquake-resistant framing, and energy-efficient insulation to meet California's Title 24 building codes. Sustainability was also baked in. Solar panels, drought-tolerant landscaping, and stormwater capture systems are integrated across the site. And unlike the original layout, the new Jordan Downs is being built with mixed-use development at its core. A central retail village is part of the plan, complete with grocery stores, cafes, and community-serving businesses. That required additional engineering for load-bearing slabs, commercial-grade ventilation, and enhanced utility access to support food service and retail operations. The project also includes new parkland, recreational facilities, and space for schools and job training centers, all of which had to be laid out on what was once a closed, fenced-off grid. On the eastern edge of San Francisco, where rusted cranes once loomed over a forgotten stretch of Shipyard, the Pier 70 redevelopment is one of the city's most ambitious megaprojects currently under construction in 2026. This historic industrial zone, nestled between the Dogpatch neighborhood and the bay, is being transformed into a vibrant waterfront community, one that blends housing, jobs, public parks, and restored heritage structures into a single cohesive district. The construction underway this year marks the most active phase of the project to date, with key milestones approaching as the site charges toward completion in the early 2030s. As of 2026, multiple parcels across Pier 70 are under simultaneous construction. Residential towers are climbing skyward, with the first phase of housing expected to be completed by 2027. These buildings will deliver nearly 1,100 homes in their initial stage, 25% of which are reserved as affordable housing. Construction crews are also working on major infrastructure upgrades across the site, including new streets, transit corridors, pedestrian paths, and shoreline protections to guard against sea level rise. The heart of the megaproject is its connection to the past. Pier 70's redevelopment in 2026 doesn't erase its history, it builds on it. Several historic buildings are being restored and repurposed. These include old machine shops and steel foundries that once supported the shipbuilding industry. In 2026, many of these structures are undergoing seismic retrofitting and interior renovations to be converted into arts venues, retail hubs, and office space for design and tech firms. The goal is to preserve the gritty industrial character of the site while making it usable and vibrant for a 21st century city. Public space is a major focus of the construction effort in 2026. Over 9 acres of parks and waterfront access points are being built across the site. The highlight will be the large central green, an expansive park framed by restored industrial sheds and framed by views of the bay. As of this year, grading, drainage, and landscaping are underway, with full park openings projected for 2028. These open spaces are being built to double as climate infrastructure, designed to absorb stormwater, manage heat, and protect the site from flooding. In addition to housing and public amenities, the commercial component of Pier 70 is actively rising. Office buildings tailored to life sciences, technology, and creative industries are under construction now, with tenants expected to begin moving in by 2027-2028. These buildings are designed with flexibility in mind, featuring adaptive floor plans, outdoor terraces, and energy-efficient systems. Construction in 2026 is focused on delivering the first phase of these workspaces, helping to establish Pier 70 as an employment hub linked directly to the city's evolving economic base. The location is also a key asset. In 2026, construction crews are coordinating with transit agencies to enhance connections between Pier 70 and the rest of the city. Muni lines, bike lanes, and pedestrian links to the nearby Dogpatch neighborhood are all part of the ongoing infrastructure work. There's also future planning underway to accommodate ferry service, which would further connect the development to the regional transit network. When fully completed in the early 2030s, the Pier 70 redevelopment will deliver over 2,000 housing units, 2 million square feet of office and commercial space, 9 acres of parks, and over 300,000 square feet of retail, cultural, and community uses. But in 2026, it's the construction activity that defines the project. Foundation work, steel framing, historic preservation, and shoreline transformation all unfolding simultaneously.
In 2026, construction begins in earnest on the Los Angeles Metro Southeast Gateway Line, a major light rail expansion aimed at delivering high-capacity transit service to some of the most densely populated and historically underserved communities in southeast Los Angeles County. Previously known as the West Santa Ana Branch Transit Corridor, this project represents one of the largest new rail corridors in the region and forms a critical part of the county's long-term Measure M mobility strategy. The project's first operational phase will span 14.5 miles, linking the existing A-Line station at Slauson in South Los Angeles to a new terminal station at Pioneer Boulevard in Artesia. This segment will include 9 new stations and is designed to serve communities across Huntington Park, Bell, Cudahy, Southgate, Downey, Paramount, Bellflower, and Artesia. As of 2026, the corridor is in the early stages of pre-construction and enabling works, with heavy utility, relocation, environmental mitigation, and corridor preparation now underway. Utility relocation is a primary focus in 2026. In multiple cities along the alignment, electrical, gas, water, and telecommunications lines are being moved to accommodate future construction of the light rail guideway and associated infrastructure. In Artesia, crews are also performing grading work and beginning access improvements in preparation for major station excavation and track installation, which is expected to ramp up in 2027. The project is being delivered under a progressive design-build model. A joint venture of Flatiron, Dragados USA, and Herzog is leading the initial pre-construction phase under a contract valued at over $997 million. This early work includes soil testing, demolition of outdated facilities, geotechnical surveys, and engineering refinements along the right-of-way. These preparatory efforts are critical to mitigating delays once full construction begins. The total cost? For the Southeast Gateway Line, Phase 1 is projected at approximately $8.6 billion. The project is being funded through a combination of local sales tax measures, including Measures R and M, along with state transportation funds and a significant request for federal support through the FTA's New Starts Capital Investment Program. Metro is targeting a full funding grant agreement from the federal government by 2027. The alignment follows a former Pacific Electric Railway corridor with portions of the route adjacent to active freight lines. In 2026, Metro and its construction partners are actively coordinating with freight rail operators to ensure clearances, right-of-way agreements, and safety systems are in place. Quiet zones, grade separation structures, and fencing are being designed, and in some areas, early site work has begun. The line will use low-floor light rail vehicles, similar to those operating on Metro's existing lines, with stations designed for full ADA accessibility. Platforms, traction power substations, and signal control infrastructure are all in the design phase in 2026, with final engineering packages expected to be released for construction bidding in 2027. South of McCormick Place, and stretching toward the edge of Lake Michigan, one of Chicago's largest proposed redevelopment megaprojects is planned on land long isolated from surrounding neighborhoods. The Bronzeville Lakefront project is a multi-phase, mixed-use development centered on the former Michael Reese Hospital site, representing a major attempt to reconnect Bronzeville to the lakefront through large-scale construction and infrastructure investment. The project area encompasses roughly 48 acres, bounded by 31st Street, 43rd Street, Lakeshore Drive, and the Metra Electric Rail Corridor. For decades, the site was dominated by the Michael Reese Hospital campus, which was demolished in the early 2010s following the city's unsuccessful bid for the 2016 Olympic Games. Demolition and site clearance marked the first major construction phase, removing dozens of buildings and leaving one of the largest undeveloped parcels on Chicago's lakefront. After demolition, the land remained largely vacant while planning efforts evolved. The Bronzeville Lakefront vision emerged as a long-term redevelopment framework rather than an immediate construction project. The master plan proposes millions of square feet of new development, including residential buildings, office and research space, institutional facilities, hotels, and retail. The scale places it firmly among the most ambitious mega projects proposed on Chicago's South Side. Infrastructure construction is central to the project's feasibility. The site requires new internal street grids, utility systems, and stormwater management infrastructure before vertical construction can occur. Because the land sits near the lake and adjacent to major transportation corridors, flood resilience and drainage engineering are critical components. Planned construction includes elevated building pads and modern stormwater detention systems designed to reduce runoff into Lake Michigan. One of the most significant proposed elements is a life sciences and innovation campus intended to anchor early development phases. This component would include laboratory buildings, research facilities, and office space designed to attract medical and biotech institutions. These buildings are expected to be among the first vertical structures constructed once infrastructure work advances, establishing employment density before residential build-out accelerates. Residential construction is planned to follow in multiple phases. The master plan allows for thousands of housing units, including a mix of market rate and affordable housing. Buildings are expected to range from mid-rise to high-rise, with height transitions designed to integrate with surrounding Bronzeville neighborhoods. Construction sequencing is intended to spread residential delivery over many years to match demand and financing availability. Transportation access is a major planning driver. The site is adjacent to Lakeshore Drive and served by the Metra Electric Line, with future improvements expected to enhance station access and pedestrian connectivity. Proposed construction includes new pedestrian bridges, improved crossings, and internal bike and transit infrastructure to reduce reliance on cars and better integrate the development with nearby communities. Unlike many downtown megaprojects, Bronzeville Lakefront places heavy emphasis on public space construction. Plans include new parks, plazas, and lakefront connections intended to extend recreational access southward. These spaces are expected to be built incrementally alongside private development, requiring coordination between public agencies and private developers. Timeline projections for Bronzeville Lakefront extend well into the 2030s. Early infrastructure and anchor projects are expected to define the first major construction phase, followed by successive waves of vertical development. Full build-out has always been envisioned as a multi-decade effort rather than a single construction cycle, reflecting both the size of the site and the complexity of funding and approvals. Rather than rising from untouched land, the new Miami-Dade Airport emerged through one of the largest continuous airport reconstruction programs ever undertaken in the United States, transforming Miami International Airport into what is effectively a rebuilt megastructure operating in real time. Miami International Airport sits west of downtown Miami and functions as the primary global aviation gateway for South Florida and Latin America. By the late 1990s, the airport's original mid-20th century terminals, roadways, and airfield systems were no longer capable of handling projected passenger growth, new aircraft sizes, or modern security requirements. Miami-Dade County responded by launching a long-term capital improvement effort, commonly referred to as the airport's New Airport Program, a reconstruction on the scale of a greenfield build while maintaining daily operations. The centerpiece of this transformation was the North Terminal Development Program, a multi-billion-dollar mega project that replaced large portions of the airport's aging infrastructure. Planning began in the late 1990s, with construction starting in the early 2000s. The program consolidated multiple older concourses into a single, linear terminal complex designed to improve passenger flow, security processing, and aircraft operations. Construction involved complete demolition of outdated concourses, utility corridors, and support buildings, followed by new foundations, structural frames, and terminal shells built adjacent to active runways and taxiways. This required phased construction sequencing to keep aircraft movements uninterrupted. New terminal structures were built using long-span steel and reinforced concrete systems capable of supporting large wide-body aircraft gates and high passenger volumes. The North Terminal was developed in multiple phases. Early phases focused on airside infrastructure, including new taxi lanes, aircraft parking aprons, and fuel hydrant systems. Subsequent phases delivered passenger processing spaces, including ticketing halls, security checkpoints, baggage handling systems, and customs facilities. The first major sections opened to passengers in the mid-2000s, with full substantial completion achieved in the early 2010s. A critical component of the new airport construction was the installation of an automated people mover system connecting the terminal to remote rental car facilities and parking structures. This required elevated guideways, stations integrated into terminal buildings, and control systems installed above active roadways. The people mover significantly reconfigured landside access to the airport. The reconstruction extended beyond terminals. Miami-Dade County invested heavily in runway rehabilitation and expansion, including pavement reconstruction, lighting upgrades, and drainage improvements. Taxiway geometry was modified to accommodate larger aircraft, such as the Airbus A380 and Boeing 777. These airfield works were completed incrementally over many years, often overnight, to avoid disrupting flight schedules. Cargo infrastructure was also rebuilt as part of the airport's Megaproject evolution. New cargo buildings, cold storage facilities, and access roads were constructed to support Miami's role as a major freight hub for perishable goods. These upgrades aligned with parallel megaprojects at Port Miami, reinforcing the county's logistics network. Security and resilience upgrades formed another major construction layer. Post-9/11 requirements led to reinforced terminal layouts, expanded security screening zones, and hardened building systems. Mechanical, electrical, and plumbing systems were replaced or upgraded to modern standards, including redundant power supplies and advanced fire protection. Flood mitigation and drainage improvements were incorporated to address Miami's climate and storm exposure. The timeline of the new Miami-Dade Airport build spans more than a decade. Major construction activity peaked between roughly 2004 and 2012, with continuous smaller projects extending beyond that period. By the early 2010s, the airport had effectively transitioned from a mid-century facility into a modern aviation megastructure, capable of handling tens of millions of passengers annually. Within the broader context of Miami's biggest megaprojects, the airport reconstruction stands alongside developments such as the Port of Miami Tunnel, Bickl City Center, and large-scale transit investments. Unlike vertical megaprojects, the airport rebuild was horizontal and systemic, requiring coordination across aviation operations, federal agencies, contractors, and airlines. By the middle of the decade, one of North Texas's earliest soccer-specific stadiums is undergoing a comprehensive reconstruction that places it firmly among Dallas area megaprojects active in 2026. The new Toyota Stadium redevelopment in Frisco represents a multi-year modernization effort focused on structural capacity, revenue generation, climate mitigation, and long-term event flexibility rather than a simple renovation. Toyota Stadium originally opened in 2005, designed for a different era of Major League Soccer and a much smaller regional population. The redevelopment project restructures the existing stadium rather than replacing it, allowing FC Dallas to continue operations while construction advances in carefully sequenced phases. By 2026, the project is deep into its most technically demanding stage, with heavy construction occurring throughout the seating bowl, concourses, and building systems. Construction work during 2026 concentrates on major structural modifications. Entire sections of the lower bowl are being demolished and rebuilt to adjust rake angles, improve sightlines, and support additional vertical loads from new premium levels above. New concrete pours and steel framing are installed in phases to maintain stadium stability, while adjacent areas remain operational. This year also includes reinforcement of existing foundations to meet updated building codes and support heavier roof and canopy systems. One of the most visible construction efforts in 2026 is the installation of expanded canopy structures. These roof elements are designed to significantly increase shaded seating, addressing long-standing heat exposure issues. The canopy construction involves large-span steel trusses, integrated lighting mounts, and future-ready broadcast attachment points. Installation is staged section by section to allow partial stadium use during the soccer season. Premium seating and hospitality spaces dominate interior construction in 2026. New club lounges, lodge boxes, and suites are being built into previously underutilized stadium volume. This requires extensive mechanical and electrical upgrades, including new air handling units, upgraded power distribution rooms, and expanded data infrastructure. Plumbing systems are also being replaced or rerouted to serve higher capacity food and beverage operations. Concourse reconstruction is another major focus in 2026. Existing concourses are being widened, regraded, and reconfigured to improve circulation and accessibility. Vertical transportation systems, including elevators and stairs, are being added or relocated to comply with modern accessibility standards. These changes require careful coordination between demolition crews, concrete teams, and utility installers to avoid service disruptions. Technology infrastructure work accelerates during 2026. Crews are installing new fiber optic backbones, wireless access systems, and security networks throughout the stadium. Dedicated broadcast rooms and control spaces are under construction to support national and international television requirements. These systems are designed to accommodate future tournaments and non-soccer events without additional major retrofits. Outside the stadium bowl, 2026 construction includes the redevelopment of surrounding plazas and entry zones. Pedestrian circulation is being improved through expanded hardscape areas, upgraded lighting, and reworked security screening layouts. These exterior improvements are engineered to support higher peak attendance and year-round events, not just match days. Sustainability measures are integrated into the 2026 construction scope. Lighting systems are being converted to high-efficiency LED fixtures. Water infrastructure is upgraded with low-flow systems, and stormwater management improvements are installed to reduce runoff during heavy rain events. Older materials removed during demolition are being recycled or reused where feasible to reduce construction waste. From a timeline perspective, 2026 represents the midpoint of the redevelopment. Structural and exterior envelope work dominates early and mid-year, while interior build-outs continue into late 2026 and beyond. Some premium areas and upgraded seating sections are expected to open in phases as construction completes, allowing incremental increases in stadium functionality. Major construction activity is scheduled to continue through 2027, with final interior finishes, technology commissioning, and operational testing extending into late 2027. Full project completion is expected between late 2027 and 2028, depending on seasonal construction constraints and event scheduling. The phased delivery approach ensures continuous stadium use while transitioning the facility to its final configuration.
Tucked just south of downtown Los Angeles, Exposition Park has always been a place of ambition. Home to world-class museums, the LA Memorial Coliseum, and the beating heart of the city's cultural and sporting life. But what's unfolding there now isn't just an upgrade. It's a full-scale transformation, timed to align with the arrival of the 2028 Olympic Games. This is the Exposition Park expansion, and it's one of the most concentrated, multi-layered megaprojects happening anywhere in the city. We're talking about more than 100 acres of dense, high-profile development, the kind of space where architecture, infrastructure, landscape, and engineering have to work in seamless coordination. And every inch of it is being reimagined, stitched together into a new kind of urban park, one that blends Olympic-scale sports facilities with civic space, transit access, and cultural presence. At the center of this expansion is the Lucas Museum of Narrative Art, an enormous, fluid, almost spaceship-like structure that defies traditional design logic. Spanning over 300,000 square feet, the building floats above the landscape on concrete pylons, allowing for an uninterrupted park to run beneath it. Engineering that vision into reality meant solving a long list of structural challenges. The museum's form curves and bends with few right angles, requiring a steel skeleton unlike any conventional grid. Every beam had to be custom fabricated. Load paths had to be recalculated from scratch. But that's only one piece. Adjacent to it, new Olympic training facilities are being added in and around the Coliseum, including athlete, housing, high-performance sports labs, and temporary structures built to IOC standards. These aren't off-the-shelf projects. Each facility must meet international competition criteria while being adaptable for post-games public use. That means flexible infrastructure, modular designs that can expand or collapse depending on future needs, and utility corridors capable of serving both a global broadcast event and a local youth sports league. A new mobility hub is also under construction, tightly integrated with the K Line, Crenshaw LAX Line, regional bus service, and pedestrian corridors linking USC, the Natural History Museum, and BMO Stadium. This isn't just about moving people. It's about rethinking access. Engineers are embedding smart traffic systems, ADA upgrades, secure bike lanes, and crowd flow modeling to handle Olympic-scale surges without overwhelming local streets. Then there's the landscape itself. More than 14 acres of new green space are being carved into the existing grid, with bioswales, permeable pavement, and stormwater recycling systems hidden beneath sculpted terrain. Everything is dual purpose. That shaded plaza? It's also an emergency egress route. That rolling hill. It's backfilled over a utilities corridor with seismic isolation joints. Every tree and trail was designed not just for beauty, but for function, cooling microclimates, guiding crowds, and managing runoff during rare but intense LA storms. Beneath the surface, the engineering complexity continues. Utility upgrades, electric, water, fiber, gas, are being laid out like a circulatory system for a future-proof urban core. Crews had to dig and trench with surgical accuracy, often working just inches away from existing structures that couldn't be moved or shut down. Phasing the construction without interrupting events at the Coliseum or the Museum District meant round-the-clock scheduling, heavy prefabrication, and just-in-time delivery logistics. The Mission Rock project is one of San Francisco's headline megaprojects under active construction in 2026. Sitting directly south of Oracle Park, on what was once a windswept sea of asphalt and overflow parking lots, this 28-acre waterfront site is being turned into a dense, walkable neighborhood that combines housing, parks, offices, and retail in one of the most high-profile real estate efforts in the city. In 2026, the project is deep in Phase 1 construction. Several major buildings have already topped out, with exterior work wrapping up and interior build-outs ongoing. Full completion of this phase is expected by late 2027. When finished, it will include nearly 1,200 new residential units, over 400 of which are permanently affordable, along with 8 acres of new public space and over 200,000 square feet of office and retail space. This megaproject isn't just reshaping a site, it's helping to redefine the southern edge of San Francisco's downtown. New streets and pedestrian promenades are already being laid out, stitched together by green infrastructure and open-air plazas designed to absorb stormwater and resist sea level rise. The waterfront park, known as China Basin Park, is being built in tandem with the buildings around it. Crews in 2026 are currently sculpting the park's shoreline and planting native vegetation, with major portions set to open by 2028. Mission Rock is a public-private partnership between the San Francisco Giants and the Port of San Francisco, and the construction in 2026 reflects a long-term vision to extend the city's core outward along the waterfront. Designed as a high-density, low-emissions community, every new structure is being built to LEED Gold or higher standards. Solar panels, all-electric systems, and smart energy grids are standard here, not just features. One of the project's architectural landmarks now under construction is the Canyon, a massive mixed-use building that blends market-rate apartments with carved terraces and retail space. In 2026, the Canyon's facade is nearly complete, and interior work is progressing toward a mid-2027 delivery. Nearby, a life sciences tower being built for the biotech sector is rising quickly, with tenants expected to begin occupancy by late 2028. What makes Mission Rock such a key part of San Francisco's 2026 megaproject landscape is its fusion of uses and its central location. Unlike isolated developments on the city's edges, this project plugs directly into the transit network and urban fabric. It's within walking distance of downtown, BART, Caltrain, and multiple Muni lines. Its completion will not only provide urgently needed housing, it will expand the city's job base and public amenities in a place long dominated by underused land. As of 2026, the construction site is a hive of activity. Steel framing, glazing, mechanical installation, and hardscape development are all occurring simultaneously across multiple parcels. Each building is being developed by a different architectural team, resulting in a diversity of forms and styles that break from the monolithic look of some other megaprojects. This is intentional. Mission Rock is designed to feel like a neighborhood, not a master plan. The entire project is expected to wrap up in multiple phases through the early 2030s, with new parcels starting construction as others finish. By the time it's fully built out, Mission Rock will include 8 acres of parks, up to 1.4 million square feet of commercial space, and space for thousands of new residents.
In 2026, several major extensions of the Bay Area Rapid Transit System are under construction, forming a critical part of Northern California's long-term transit infrastructure strategy. The largest and most technically complex is the Silicon Valley Phase 2 extension, a 6-mile expansion of BART service from Berryessa, North San Jose, to downtown San Jose and Santa Clara. This project is being led by the Santa Clara Valley Transportation Authority in partnership with BART and is a federally funded, multi-billion-dollar endeavor. Construction in 2026 is fully active along the entire Phase 2 alignment. The project includes 4 new stations: 28th Street, Little Portugal, downtown San Jose, Diridon, and Santa Clara. Approximately 5 miles of the alignment will be constructed using a single-bore tunnel, 45 feet in diameter, making it one of the largest subway tunnel sections in North America. In 2026, tunneling operations are scheduled to begin following completion of launch shaft excavation and assembly of the tunnel boring machine. Shaft construction and staging zones are already established at multiple sites, including the Western Portal near Diridon Station. The downtown San Jose station, which will be built underground, presents specific challenges due to its depth and proximity to active utilities, heritage buildings, and seismic zones. In 2026, deep excavation, support of excavation walls, and early concrete pours are underway. Similar substructure work is progressing at 28th Street and Diridon, where retained cut and mined station boxes are being constructed. Cut and cover methods are being used at the Santa Clara station, which will serve as the new western terminus of the extension and will include a surface-level tail track and storage tracks. The entire Phase 2 extension is projected to open for revenue service by 2036, with major civil work and tunneling expected to conclude by the early 2030s. The project's integration with existing transit hubs, including Caltrain, Amtrak, VTA Light Rail, and future California High-Speed Rail at Diridon, is a key element of the design. In 2026, intermodal design coordination is ongoing between BART, VTA, Caltrain, and city agencies to synchronize platforms, vertical circulation, and fare systems. Elsewhere in the Bay Area, BART is continuing with other network improvement projects in 2026. This includes planning and pre-construction for the potential extension to Livermore along the I-580 corridor. Although not yet in full construction, right-of-way acquisition and environmental reviews are active. This corridor is intended to close a critical gap between Dublin, Pleasanton, and the Tri-Valley region. Throughout Central and Southern California in 2026, university campuses are undergoing large-scale construction to accommodate rising enrollment, research expansion, and updated sustainability mandates. These developments span multiple University of California and California State University institutions, with a focus on housing, laboratories, medical infrastructure, and renewable energy integration. At the University of California, Merced, construction continues on multiple academic and housing facilities under the 2020 Project Phase 2, expanding the campus's capacity well beyond its original footprint. In 2026, vertical construction is active on new science and engineering buildings, along with residential halls that will add over 1,000 new beds by 2027. These additions support UC Merced's long-term goal to serve over 15,000 students and enhance its research output in agricultural technology and climate science. Beneath Chicago's streets, rivers, and neighborhoods lies one of the largest underground civil engineering systems ever built, a megaproject whose scale rivals any visible skyscraper or transit expansion in the city. The Tunnel and Reservoir Plan, commonly known as TARP or the Chicago Deep Tunnel, is a decades-long infrastructure program designed to control flooding, reduce sewer overflows, and protect regional waterways. The origins of TARP trace back to the mid-20th century when rapid urban growth combined stormwater and sewage into a single system that frequently overwhelmed treatment plants. Heavy rainfall routinely forced untreated wastewater into the Chicago River system and Lake Michigan. Planning for a permanent solution began in the 1960s, with construction formally launching in 1975 under the oversight of the Metropolitan Water Reclamation District of Greater Chicago. The core of the project consists of more than 100 miles of deep rock tunnels excavated between 150 and 300 feet below ground. These tunnels range from 9 to over 30 feet in diameter and were bored through solid dolomite bedrock using tunnel boring machines customized for long-duration, high-pressure excavation. Construction occurred in phases over several decades, with tunneling largely completed by the early 2000s. The tunnels function as massive underground storage conduits. During storms, combined sewage is diverted from surface sewers into the deep tunnel network, preventing street flooding and uncontrolled discharges into waterways. Once storms pass, the stored water is gradually pumped to treatment plants for processing. This operational strategy required the construction of dozens of drop shafts, some wider than 30 feet, and extending hundreds of feet downward, connecting surface infrastructure to the tunnel system. A second major component of TARP is its reservoir system, which represents the most visible and recent phase of construction. These reservoirs were designed to provide additional storage capacity beyond the tunnels. The largest of these is the Thornton Composite Reservoir, built within a former limestone quarry south of the city. Construction began in the late 1990s, with phased completion allowing partial operation before the full reservoir was finished. When fully complete, Thornton provides over 7 billion gallons of storage, making it one of the largest stormwater reservoirs in the world. Additional reservoirs include the McCook Reservoir in western Cook County. This facility has been constructed in stages, with the first phase becoming operational in the late 2010s. Full completion, including its second major stage, is scheduled for the mid-2020s. Once finished, McCook will add approximately 10 billion gallons of combined stormwater and sewage storage capacity to the system, significantly increasing flood protection for large portions of Chicago and surrounding suburbs. Along a former industrial corridor stretching between Lincoln Park and Bucktown, one of Chicago's most ambitious redevelopment megaprojects has been planned on land that sat underutilized for decades. Lincoln Yards is a proposed large-scale, mixed-use development intended to transform roughly 53 acres along the north branch of the Chicago River into a new urban district, combining residential, commercial, infrastructure, and public space construction. The site historically housed steel mills, manufacturing plants, and later, large-scale storage and light industrial uses. Much of the land required extensive environmental remediation due to contamination from its industrial past. Preparatory work over the past several years has focused on soil cleanup, demolition of remaining industrial structures, and riverbank stabilization, which represent the earliest construction-related activities tied to the project. Beneath Biscayne Bay, hidden from the skyline that defines Miami's megaproject boom, the Port of Miami Tunnel represents one of the most complex and consequential infrastructure projects ever built in South Florida. The Port of Miami Tunnel was designed to directly connect Dodge Island, home to Port Miami, with the interstate highway system, creating a dedicated underground freight corridor between the port and Interstate 395 and Interstate 95. Before the tunnel, cargo trucks were forced to move through downtown Miami streets, creating chronic congestion, safety issues, and delays that constrained the port's growth. The tunnel fundamentally restructured how goods move through the city, making it a critical component of Miami's broader mega-project transformation. Planning for the tunnel began decades before construction, with serious development efforts accelerating in the early 2000s as Port Miami expanded into a major global cargo and cruise hub. Construction officially began in 2010 after years of environmental review, financing negotiations, and engineering studies. The project was delivered through a public-private partnership, an uncommon approach at the time for U.S. transportation megaprojects, involving the Florida Department of Transportation and a private concessionaire responsible for design, construction, financing, and long-term operation. The construction scope centered on 2 parallel tunnel tubes, each approximately 3,900 feet long, bored beneath Biscayne Bay. The tunnels were excavated using a massive tunnel boring machine specifically designed to operate in Miami's challenging geology, which consists of porous limestone, sand, and a high water table. The tunnel boring machine, weighing thousands of tons, was launched from Watson Island and advanced underwater toward Dodge Island, cutting through bedrock while simultaneously installing precast concrete liner segments to stabilize the tunnel walls. Excavation operations required continuous groundwater management and precise pressure control to prevent collapse or water intrusion. The tunnel alignment passed beneath active shipping channels, requiring careful coordination to avoid disrupting port operations and marine traffic. Spoil material removed during tunneling was transported and processed without interfering with surrounding urban and maritime infrastructure. In addition to the underwater tunnels, the project included extensive cut and cover construction on both ends. On Watson Island and Dodge Island, large access portals were excavated, requiring dewatering systems, retaining walls, and deep foundations to support the tunnel entrances. New roadway interchanges were built to connect the tunnel directly to I-395, eliminating truck traffic through surface streets in downtown Miami. Construction also included advanced ventilation buildings, fire suppression systems, emergency cross passages between tunnel tubes, and real-time monitoring systems. These safety features were essential to meet federal highway tunnel standards and ensure continuous operation in a hurricane-prone region. The tunnel was engineered to withstand storm surge, seismic forces, and long-term exposure to saltwater conditions. The project faced multiple technical and schedule challenges during construction. Delays occurred due to mechanical issues with the tunnel boring machine, groundwater infiltration events, and the complexity of working beneath an active port and bay. Despite these challenges, tunneling was completed in 2013, marking one of the most technically demanding phases of the project. Following structural completion, several years were dedicated to roadway finishing, systems installation, testing and commissioning, ventilation, lighting, traffic control, and emergency systems underwent extensive testing before the tunnel was open to traffic. The Port of Miami Tunnel officially opened in August 2014, completing a construction timeline of roughly 4 years. Within the context of Miami's biggest mega projects, the Port of Miami Tunnel stands apart from high-rise developments like Panorama Tower or Bickl City Center. Rather than reshaping the skyline, it reshaped the city's logistical foundation. By removing thousands of trucks per day from downtown streets, the tunnel enabled parallel megaprojects in residential, commercial, and cultural development to proceed without freight congestion, limiting growth. Set slightly apart from the historic core of downtown Dallas, the Bank of America Tower at Parkside represents one of the most prominent vertical megaprojects under construction in the Dallas region in 2026. Rising within the Park District near Clyde Warren Park, the tower is positioned as a next-generation commercial office building designed to consolidate major corporate operations while redefining the northern edge of the central business district. The project consists of a high-rise office tower with a large floor plate, advanced building systems, and integrated public realm improvements. It is designed to accommodate a single major anchor tenant while also supporting multi-tenant flexibility. The structure replaces older, lower-density development, reflecting a shift toward taller, more efficient office buildings in Dallas's core employment zones. By 2026, the Bank of America Tower at Parkside is firmly in its vertical construction phase. Structural framing dominates activity throughout the year, with reinforced concrete cores and post-tensioned floor slabs rising steadily above street level. Tower cranes remain on site through most of 2026 to support formwork, rebar placement, and concrete pours as the building progresses floor by floor. Facade installation becomes a major focus during 2026. Curtain wall systems, consisting of high-performance glass and metal panels, are installed from the lower levels upward as the structure tops out. This work is carefully sequenced with interior construction to allow mechanical and electrical rough-ins to follow closely behind the enclosure of each completed floor. The facade is engineered for solar performance, glare reduction, and long-term energy efficiency. Interior construction accelerates significantly during 2026. Mechanical, electrical, and plumbing systems are installed across multiple levels simultaneously. This includes high-capacity HVAC systems designed for dense office occupancy, advanced air filtration, and smart building controls. Electrical infrastructure includes redundant power distribution and backup systems consistent with large financial and corporate tenants. Elevator installation is another critical task, underway in 2026. High-speed elevator shafts are completed within the concrete core, followed by cab installation, guide rails, and control systems. These systems are designed to minimize wait times while serving a tall structure with large floor plates and high daily occupancy. Ground-level construction remains active throughout 2026 as well. The tower integrates structured parking, loading docks, and secure service access beneath and adjacent to the building. Streetscape improvements, including widened sidewalks, landscaping, and pedestrian connections to nearby parks and transit routes, are constructed alongside vertical progress. These elements are coordinated with city infrastructure upgrades to minimize disruption in a dense urban environment. Life safety systems are installed and tested in phases during 2026. Fireproofing, sprinkler systems, smoke control, and emergency power infrastructure are integrated as each floor reaches substantial completion. These systems must be commissioned incrementally to support ongoing construction above occupied or enclosed levels. From a scheduling perspective, 2026 represents the midpoint to late middle phase of the project timeline. Structural topping out is expected either during or shortly after 2026, depending on sequencing and weather conditions. Once the structure is complete, focus shifts more heavily toward interior finishes, tenant build-outs, and systems commissioning. Major construction activity continues into 2027, with interior finishes, lobby construction, exterior plaza completion, and final facade detailing extending well beyond the structural phase. Testing and commissioning of building systems, including elevators, HVAC, and security systems, are expected to continue through late 2027.
Where the Port of Los Angeles meets the open Pacific, a vast transformation is underway. Once a place defined by rusted cranes and abandoned warehouses, San Pedro's historic waterfront is being reimagined as a massive public destination. This is West Harbor, a $500 million redevelopment project that's reshaping 42 acres of prime harborfront land into one of the largest and most ambitious waterfront revitalizations in California history. For decades, the San Pedro waterfront was a place of industry. Cargo ships, rail lines, and container yards dominated the landscape, cutting the community off from its own shoreline. The ocean was always there, visible but unreachable. The idea behind West Harbor was radical in its simplicity. take land that had long been the realm of cranes and commerce and return it to the people. Replace the shipping yards with open promenades. Tear down the fences, open the gates. But turning a gritty, industrial port into a modern, urban waterfront park isn't just a matter of cosmetics. It's an enormous engineering challenge. Beneath the surface, the ground itself needed rebuilding. Years of marine traffic, heavy equipment, and salt exposure had weakened bulkheads and corroded old pilings. Before a single restaurant could open, crews had to stabilize the soil, drive hundreds of deep foundation supports, and upgrade the harbor's edge to withstand both tidal surges and seismic shocks. At the heart of the project is a massive promenade that wraps along the water, designed not just for pedestrians, but for resilience. The concrete pathways are elevated to anticipate sea level rise, with drainage systems engineered to handle storm surges from both land and ocean. New docks are being constructed to support visiting ships and harbor cruises, each one designed with floating gangways that rise and fall with the tides, maintaining access even in extreme conditions. West Harbor isn't just infrastructure, it's experience. The development includes over 150,000 square feet of space for retail, dining, and entertainment, with anchor tenants ranging from artisan markets to major restaurants. A 6,200-seat outdoor amphitheater is being built directly on the waterfront, engineered to deliver concert-quality acoustics in a coastal environment, where sound bounces unpredictably off water and wind. Engineers had to design the stage foundation to accommodate both musical events and the occasional pounding from Pacific storms, using vibration damping, materials, and reinforced steel substructures. All of this, performance spaces, restaurants, shops, sits on land reclaimed from decades of industrial use. That meant a full environmental remediation process, involving soil testing, removal of contaminated fill, and installation of modern stormwater systems to prevent runoff from polluting the bay. A particularly complex element was integrating the new West Harbor seamlessly with the surrounding transportation network. This meant widening roads, building new intersections, and coordinating with nearby freight operations, all while preserving the historic landmarks that give San Pedro its identity. The historic battleship Iowa, docked nearby, had to be factored into every phase of design, ensuring visitor access remained open during construction. The engineering teams also had to work in parallel with the Port of LA's ongoing operations, scheduling pile driving and crane activity to avoid disrupting maritime logistics. Even as the heavy machinery rolls and concrete is poured, the bigger vision is already taking shape. This isn't just about leisure. It's about reconnecting a city with its coastline. For generations, San Pedro's waterfront was a wall of industry. West Harbor turns it into a front porch. Candlestick Point and Hunters Point Shipyard are among the most active megaprojects in San Francisco as of 2026. Spanning more than 700 acres along the city's southeastern shoreline, this redevelopment effort is in full swing, reshaping two long-neglected sites into a new urban district. Construction is progressing across multiple parcels, with new streets, housing blocks, and parks taking shape, setting the stage for what will become one of the largest residential and commercial expansions in San Francisco's modern history. At Candlestick Point, where the old stadium was demolished years ago, heavy machinery is grading land for the first wave of residential and retail construction. Multiple mid-rise buildings are rising along a newly gridded street layout. These early phases, expected to complete between 2027 and 2029, will include thousands of homes, many designated as affordable, as well as the backbone of a future retail corridor and public transit connections. Parks and green infrastructure are being built alongside housing, integrating sea level rise protections and climate-resilient landscaping directly into the urban form. To the north, at Hunters Point Shipyard, development is further along. Phase 1 construction is already well underway, with completed townhomes and condos beginning to fill with residents. Additional parcels are actively under construction in 2026, adding new units monthly. Commercial spaces, artist studios, and civic buildings are also under development. Part of the project's goal to restore not just housing, but economic vitality to a part of the city long cut off from opportunity. When fully built out in the early 2030s, the combined Candlestick Hunters Point project will deliver over 12,000 new homes, more than 300 acres of open space, and millions of square feet of office, retail, and cultural uses. It's a complete neighborhood emerging from land that was, for decades, contaminated, fenced off, and largely abandoned. What's distinctive about this project in 2026 is its physical and social scale. This isn't a small infill development or a single commercial tower. It's a city-scale expansion happening within the city limits. Infrastructure is being laid from scratch. Power grids, sewer lines, transit loops, and broadband networks are all part of the foundational work occurring now. Major sections of waterfront are being rebuilt with ecological restoration in mind, with plans for habitat zones, walking trails, and public piers that will eventually reconnect residents with the shoreline. Affordable housing is a central element of the development, and 2026 marks a critical point as the first large wave of affordable units nears completion. These are being reserved in part for legacy residents of Bayview Hunters Point, addressing historic displacement and economic exclusion. Community input remains part of the planning process, particularly in shaping local hiring programs and cultural preservation efforts. Construction challenges remain. Environmental safety is closely monitored due to the site's naval and industrial history. Some parcels require more remediation than others, which is influencing the pace of development. But in terms of raw activity, cranes, crews, and square footage under construction, Candlestick Point and Hunters Point Shipyard rank among the most dynamic megaprojects in San Francisco right now.
The San Joaquin Valley is one of the most active frontiers for large-scale renewable energy deployment in the United States. Central to this transformation is the Westlands Solar Park, a vast solar generation complex occupying former agricultural land in western Fresno and Kings counties. At full build-out, the project is planned to exceed 2,700 megawatts of solar photovoltaic generation capacity, with enough output to power over 1.2 million homes annually. Construction activity at Westlands is ongoing in multiple phases in 2026. Several hundred megawatts of new capacity are being installed this year alone, involving tracker-mounted solar panels, inverter stations, and substation upgrades across various parcels of the site. The terrain consists of retired farmland, much of it previously deemed unusable due to salt buildup and water supply restrictions. These parcels are being repurposed for renewable energy under a land use framework coordinated with the Westlands Water District and state energy planners. New transmission infrastructure is also under construction in 2026 to connect additional generating blocks to the California Independent System Operator grid. This includes expansion of the Gate substation and integration of newly completed collector substations. Interconnection capacity is being increased to accommodate not only current solar projects, but also future energy storage systems that are now part of long-range build-out plans. In parallel with solar generation, battery energy storage is entering the construction pipeline. In 2026, multiple developers are installing utility-scale battery systems adjacent to solar arrays designed to store surplus daytime generation, and discharge it during peak evening demand. These lithium-ion systems are being integrated directly with grid controls, supporting load balancing and reducing reliance on natural gas peaker plants. The development at Westlands is part of a larger regional shift. In 2026, the Western San Joaquin Valley hosts more than a dozen large renewable energy projects in various stages of permitting, construction, or operation. This includes both standalone solar fields and hybrid facilities with co-located batteries. Projects are distributed across counties, including Fresno, Kings, Kern, and Tulare, taking advantage of high solar irradiance, flat terrain, and proximity to major transmission corridors, such as Path 15 and the California-Oregon intertie. Permitting processes in 2026 have been streamlined under the state's renewable energy acceleration mandates, particularly those tied to SB 100 and the state's goal of reaching 100% zero-carbon electricity by 2045. Projects in Westlands benefit from environmental pre-clearance under the Renewable Energy Transmission Initiative, which has designated this area as a high-priority renewable energy zone. As a result, timelines from permitting to groundbreaking have shortened significantly in recent years. Employment across these projects in 2026 supports hundreds of construction jobs in electrical, civil, and mechanical trades. Labor agreements ensure prevailing wages and workforce training, while local agencies coordinate with developers on road improvements and service access. Equipment staging, panel deliveries, and interconnection work are active throughout the region, with multiple utility contractors working simultaneously across different sites. On Chicago's south branch of the Chicago River, a new sports and urban development megaproject is being proposed that would add a purpose-built soccer stadium to the city's expanding list of large-scale construction efforts. The new Chicago Fire Stadium, planned as part of the broader The 78 development, represents a significant shift in how professional soccer infrastructure is integrated into Chicago's urban core. The project centers on the construction of a soccer-specific stadium for Chicago Fire FC, designed to replace the club's current use of Soldier Field. The proposed stadium would seat approximately 22,000 to 25,000 spectators, aligning with modern Major League Soccer standards that prioritize compact design, fan proximity to the field, and operational efficiency. The stadium is planned to be fully enclosed on all sides, with a roof structure intended to improve acoustics and weather protection while maintaining open sight lines to the surrounding cityscape. The site is located on a long vacant 62-acre parcel south of Roosevelt Road, historically used as rail yards and industrial land. This area has been undergoing years of environmental remediation and infrastructure planning. The stadium would occupy a portion of the land designated for entertainment and civic uses within the 78 Master Plan, a larger mixed-use mega-project that includes residential towers, office buildings, research facilities, and riverfront public space. Construction for the stadium has not yet begun, but the proposal outlines a privately financed project, primarily funded by the team's ownership group. Estimated costs range in the hundreds of millions of dollars, reflecting not only the stadium itself, but also associated infrastructure such as utility connections, riverwalk improvements, and transit access enhancements. The intent is to minimize direct public subsidy while leveraging existing city investments already committed to the 78's foundational infrastructure. From a construction standpoint, the stadium would involve deep foundation work due to the site's industrial past and proximity to the river. Soil stabilization, pile driving, and flood mitigation measures would be required before vertical construction could begin. The building structure is expected to combine reinforced concrete lower levels with a steel superstructure supporting seating tiers and roof elements. Prefabrication is likely to be used for seating bowls and roof components to reduce on-site construction time. Timeline projections place the earliest possible start of major construction in the mid to late 2020s, contingent on final approvals, design completion, and coordination with adjacent developments. If approved on an accelerated schedule, construction would likely take approximately 2 to 3 years, suggesting a potential opening near the end of the decade. This would align the stadium's debut with later phases of the 78's build-out, rather than its initial residential and office towers. The stadium's integration into Chicago's transportation network is a key planning component. The site is within walking distance of existing CTA rail lines and metro services, and future transit enhancements tied to the 78 could further improve access. Pedestrian bridges, expanded sidewalks, and riverwalk connections are anticipated as part of the surrounding public realm improvements, allowing the stadium to function as a year-round anchor rather than a single-use venue. From an urban planning perspective, the project marks a departure from the city's previous approach to large sports facilities. Instead of placing the stadium on the urban periphery or adapting an existing multi-purpose venue, this mega project embeds a professional sports facility directly into a dense, mixed-use district. This allows stadium operations to support nearby businesses, housing, and public spaces, extending economic activity beyond match days. The proposed stadium also addresses long-standing operational challenges for Chicago Fire FC. Soldier Field's size, configuration, and scheduling constraints have limited matchday atmosphere and revenue potential. A dedicated stadium would provide full control over scheduling, sponsorship integration, and fan experience, while also reducing operational costs associated with renting a large NFL venue. Rising from the western edge of downtown Miami, Panorama Tower represents one of the most consequential vertical construction efforts in the city's modern history and stands as a defining chapter in Miami's era of megaproject development. Panorama Tower is an 85-story, mixed-use skyscraper located at 1101 Bickl Avenue, positioned at the intersection of Bickl downtown and the Miami Health District. When it topped out, it became the tallest building in Florida, reaching a structural height of approximately 868 feet. Construction began in 2013, and the tower was officially completed in 2018, following a multi-year development cycle that coincided with Miami's rapid transformation into a global, high-rise city. The project was developed by Florida East Coast Realty, a company with deep historical ties to the state's infrastructure and urban development. Panorama Tower was conceived not as a single-purpose building, but as a vertically integrated megastructure combining residential, office, hotel, and retail space within one footprint. This approach reflected a broader shift in Miami construction during the 2010s, where land constraints and economic growth pushed developers toward dense, mixed-use, vertical solutions. The construction scope of Panorama Tower was extensive and technically demanding. The tower contains more than 2.8 million square feet of total built area. Its program includes approximately 821 residential units, over 200,000 square feet of Class A office space, a 208-room hotel, and significant ground-level retail and parking infrastructure. The building's foundation required deep piling systems designed to anchor the structure into Miami's limestone bedrock, a critical engineering challenge given the city's high water table and coastal soil conditions. Structurally, Panorama Tower uses a reinforced concrete core and shear wall system, a method commonly employed in super tall residential towers, but executed here at unprecedented scale for Florida. High-strength concrete mixers were required to handle vertical loads at extreme heights, and the construction sequence demanded precise coordination to maintain schedule while pouring floor plates at increasing elevations. Wind engineering played a central role in the design, with the tower engineered to withstand hurricane force wind loads common to South Florida. Construction logistics were particularly complex due to the site's proximity to major roadways and active urban districts. Crane operations, concrete deliveries, and vertical material transport had to be tightly managed to minimize disruption to surrounding neighborhoods. At peak construction, hundreds of workers were on site daily, contributing to one of the largest active construction projects in Miami at the time. The timeline of Panorama Tower closely mirrors Miami's broader construction boom. Groundwork and foundation activities began shortly after the 2013 groundbreaking. Vertical construction accelerated between 2015 and 2017, during which the tower surpassed all other buildings in the state in height. Topping out occurred in late 2017, marking a symbolic milestone for Miami's skyline. Interior build-out, systems commissioning, and phased occupancy continued into 2018, when the project reached full completion. Within the context of Miami's megaproject landscape, Panorama Tower stands alongside developments such as Bickl City Center, Miami World Center, and the ongoing expansion of the downtown and Bickl corridors. Unlike large multi-block projects, Panorama Tower condensed megaproject scale into a single vertical structure, demonstrating how Miami's growth could be achieved upward rather than outward. The building also marked a shift in how Miami approached mixed-use density. By stacking residential, hospitality, and commercial uses, Panorama Tower reduced reliance on horizontal sprawl and car-dependent layouts. Its parking systems, mechanical floors, and vertical circulation were engineered to support thousands of daily occupants within a single building envelope. At the center of North Texas's expanding regional rail network, the DART Silver Line stands as one of the most complex transportation megaprojects under construction in the Dallas region in 2026. Unlike traditional light rail lines, the Silver Line is being delivered as a commuter-style corridor designed to connect suburban employment centers, major airports, and existing rail systems across multiple cities in Collin, Dallas, and Tarrant counties. The Silver Line is a roughly 26-mile east-west rail corridor stretching from Shiloh Road in Plano to DFW Airport North Station. It repurposes and upgrades an existing freight rail right-of-way, requiring extensive coordination between passenger rail construction and ongoing freight operations. This shared corridor condition defines much of the construction activity occurring in 2026, making the project significantly more complex than greenfield rail lines. By 2026, the Silver Line is firmly in its peak construction phase. Track installation and rehabilitation are ongoing across multiple segments, including full replacement of rail, ties, ballast, and drainage systems to meet passenger rail standards. In several areas, parallel tracks are being added or extended to allow freight and passenger trains to operate simultaneously without service conflicts. These works require nighttime construction windows and precise scheduling to minimize disruption. Station construction is a major focus during 2026. All planned stations serving Plano, Addison, Carrollton, Capel, and DFW Airport are in various stages of vertical construction. Platform structures, canopies, elevators, stairways, and pedestrian bridges are being built concurrently at different sites. In 2026, crews are installing structural steel, pouring elevated platforms, and beginning architectural finishes at stations that reached foundation completion in earlier years. Grade crossing reconstruction defines another major category of 2026 construction. Dozens of roadway crossings along the corridor are being rebuilt or upgraded with new signaling systems, gates, medians, and roadway geometry. Some crossings are being closed or consolidated entirely to improve safety and reduce long-term maintenance. These works require coordination with local municipalities and involve phased traffic shifts that extend throughout the year. Bridge and structure work continues through 2026 at multiple locations. Existing rail bridges are being widened, reinforced, or replaced to support increased rail traffic and modern load requirements. In flood-prone areas, embankments and culverts are being rebuilt to improve resilience against extreme weather events. These civil works represent some of the most capital-intensive portions of the project. Systems installation accelerates significantly during 2026. Crews are deploying signaling and train control systems designed for higher speed regional rail service. This includes centralized traffic control infrastructure, communication systems, and safety monitoring equipment. Fiber optic networks are being installed along the corridor to support real-time operations, dispatching, and passenger information systems. From a timeline perspective, 2026 is a transition year between heavy civil construction and operational readiness. While earthwork and major structures dominate early phases of the project, 2026 sees a shift towards systems integration, station completion, and corridor-wide testing preparation. Track work and signaling installation continue into 2027, followed by extensive testing and certification. Revenue service is not expected to begin in 2026. Instead, late 2026 and 2027 are dedicated to system testing, operator training, safety certification, and coordination with freight rail partners. Full passenger service is anticipated after completion of these phases, with opening targeted in the latter part of the decade, contingent on testing and regulatory approval timelines. Within the broader context of Dallas megaprojects under construction in 2026, the DART Silver Line is distinct for its regional impact rather than visual prominence. It directly connects major job centers, suburban cities, and DFW Airport without requiring transfers through downtown Dallas. Its construction reshapes an existing rail corridor into a modern passenger system, expanding mobility options across one of the fastest-growing metropolitan regions in the United States.
The Metro Regional Connector is just 1.9 miles long, but its impact ripples across the entire Los Angeles basin. Beneath the chaotic sprawl of downtown, this subterranean link has silently transformed the backbone of the city's transit network. Not with flashy architecture or sweeping overpasses, but with precision tunneling and deep engineering ambition. It's a megaproject built not to be seen, but to be felt, every time a train glides through the city uninterrupted. Before this connector existed, Los Angeles had a problem. Its growing light rail system, the A, E, and L lines, stopped short of being truly regional. Trains terminated downtown, forcing commuters to transfer between lines, often in disconnected stations, wasting time and discouraging use. The system worked technically, but it didn't flow. It didn't breathe. The regional connector changed that. By boring two parallel tunnels through the dense urban core and tying together these once isolated lines, it created the first true one-seat ride across the county. Now a passenger can board in Azusa and ride directly to Long Beach. East Los Angeles to Santa Monica, no transfers, no transfer platforms, just a straight shot through the city's heart. It's a small piece of track, but a massive leap in connectivity. But connecting three major lines under a century-old city is anything but simple. Downtown LA is layered in complexity, filled with pre-existing tunnels, water mains, sewers, building foundations, earthquake faults, and a living, breathing population above. To carve a clean path through all of it, engineers had to think in three dimensions, navigating not just forward, but over, under, and around everything in their way. The answer came in the form of two tunnel-boring machines, Angeli and Elsie. Each one was a 1,000-ton beast, stretching over 400 feet long, with rotating cutter heads capable of grinding through soil, rock, and buried urban history. But the real trick wasn't speed, it was control. Tunneling through this part of LA meant passing just feet beneath sensitive structures like the historic Broadway corridor and active subway lines, where even the slightest misalignment could cause cracks or settlement. So crews worked slowly, methodically. Pressurized faces on the TBMs stabilized the ground ahead. Real-time monitoring systems tracked every vibration and movement, sending feedback to operators above. In some segments, the margin for error was less than an inch. It was engineering done with surgical precision, buried beneath a city that never stopped moving. At the surface, the work was just as intense. 3 brand new underground stations were constructed: Little Tokyo Arts District, Historic Broadway, and Grand Avenue Arts, Bunker Hill. Each of them had to be excavated in tight quarters, often amid live traffic, aging buildings, and pedestrian zones. The Little Tokyo station posed one of the greatest challenges. Crews had to demolish the existing above-ground station, reroute the tracks underground, and do it all while preserving the cultural heart of a vibrant neighborhood. Buried beneath the surface of San Francisco's downtown in 2026 is one of the city's most consequential megaprojects under construction: the Portal, also known as the Downtown Rail Extension. This massive underground infrastructure project is finally being realized after decades of delays, aiming to connect Caltrain and eventually California's high-speed rail directly to the Salesforce Transit Center. As of this year, excavation work is ramping up, tunneling contracts are active, and the city is fully committed to completing the extension by the early 2030s. In 2026, the Portal is a hive of subterranean activity. Tunnel boring preparations are in progress, utility relocation is underway, and major downtown streets are experiencing stage disruptions as crews create access points for the underground guideways. It's one of the most complex transportation builds in the Bay Area, requiring coordination beneath some of the densest blocks in the city. Once complete, this megaproject will deliver a seamless rail connection from the peninsula and Central Valley straight into the financial core of San Francisco. The project involves building approximately 1.3 miles of new track, mostly underground, to link the existing Caltrain line near 4th and King with the Salesforce Transit Center. In 2026, the staging areas at both ends of the project are fully operational. Pile driving, shoring walls, and structural reinforcements are all happening in real time as the city begins to carve out the physical corridor that will carry thousands of passengers daily. Construction in and around Townsend, 2nd Street, and the south of Market area is active and accelerating, with visible impacts above ground and substantial progress being made below it. The Portal isn't just a rail project, it's a regional unlock. In 2026, Caltrain still terminates at 4th and King, about a mile short of downtown. That last mile has long been the missing link in Bay Area transit. By closing that gap, this project will plug regional rail directly into San Francisco's business core, reducing car dependency and reshaping how people move across the region. When complete, the Portal will allow Caltrain riders to disembark in the heart of the city and will set the stage for future high-speed rail service to run directly from Los Angeles to downtown San Francisco, without transfers. The current timeline targets a completion date in the early 2030s, with most heavy construction expected to occur between 2026 and 2030. In the context of San Francisco's other megaprojects under construction right now, the Portal stands out for its invisibility. Most of the work is happening underground, but the scale of its impact will rival that of any tower or waterfront redevelopment. Cost is high, risk is real, and coordination is intense. Crews are navigating under live utilities, major foundations, and transit lines. Every foot of tunnel requires precision, and every stage of construction must account for seismic resilience, waterproofing, and integration with existing BART and MUNI infrastructure. In 2026, engineering teams are deep into geotechnical work and soil stabilization, preparing for the eventual tunnel boring operations that will begin in earnest in 2027.
Occupying the geographic and economic heart of Miami's financial district, Bickl City Center stands as one of the largest and most technically ambitious urban megaprojects ever constructed in South Florida. Bickl City Center is a multi-phase, mixed-use development spanning roughly 4 city blocks in the Bickl neighborhood. The project was conceived to redefine high-density urban construction in Miami by combining retail, office, residential, hospitality, and transit infrastructure within a single integrated footprint. Planning began in the late 2000s, with the formal development advancing in the early 2010s as Bickl rapidly transitioned from a low-rise banking district into a vertical urban core. Construction officially began around 2012, starting with extensive site preparation and demolition of existing structures. The scale of the project required a complete reconfiguration of underground utilities, including new water, sewer, electrical, and telecommunication systems capable of supporting millions of square feet of development. Deep excavation followed, with dewatering systems installed to manage Miami's high groundwater levels during foundation work. At the structural level, Bickl City Center required a complex system of reinforced concrete cores, transfer slabs, and podium structures. The development includes multiple residential towers, 2 major office towers, a hotel tower, and a large retail and entertainment podium. Each tower was built using high-strength concrete and deep pile foundations drilled into limestone bedrock to handle vertical loads and wind forces. One of the defining construction features of Bickl City Center is the climate ribbon, an elevated architectural canopy spanning the retail core. This structure required long-span steel framing and custom fabricated components designed to provide shade, ventilation, and rain protection in a subtropical climate. Installation of the climate ribbon occurred during the later stages of podium construction and required precise sequencing above active work zones. The retail podium itself was constructed as a multi-level structure occupying the center of the site. Large column-free interior spaces were achieved through the use of transfer beams and post-tension slabs. Mechanical and electrical systems were embedded within the podium to serve both retail tenants and the towers above, reducing redundancy and optimizing space. Office construction included 2 Class A towers designed to modern seismic, wind, and hurricane standards. These towers required curtain wall systems engineered for high wind resistance and solar control. Interior build-outs were completed after core and shell construction, with phased tenant occupancy beginning shortly after structural completion. Residential construction was delivered across several towers, each with distinct layouts but shared infrastructure systems. Vertical construction of these towers progressed concurrently, requiring careful coordination of cranes, concrete pours, and material logistics within a confined urban site. Residential units began delivering in phases starting in the mid-2010s. Hospitality construction included a high-rise hotel tower integrated into the overall podium. This required specialized structural and mechanical design, including back-of-house service zones, conference facilities, and rooftop amenities. Hotel construction was completed alongside residential phases to align with the overall project schedule. Transit integration was a major component of Bickl City Center's construction scope. The project directly connects to the Metro Mover system, requiring new station interfaces, elevated walkways, and structural modifications to existing transit infrastructure. These connections were built while the Metromover remained operational, adding complexity to sequencing and safety planning. The construction timeline unfolded in defined phases. Major vertical construction occurred between approximately 2013 and 2015. The retail component of Bickl City Centre opened in late 2016, marking a key milestone for the project. Office and residential towers reached substantial completion around the same period, with additional residential deliveries extending into 2017. From a megaproject perspective, Bickl City Centre was notable for its centralized construction management and financing structure, allowing multiple buildings to rise simultaneously rather than sequentially. This approach shortened the overall development timeline, but increased coordination demands across trades and contractors. One of the most complex airport infrastructure undertakings in the United States is nearing critical completion at Los Angeles International Airport in 2026. The Landside Access Modernization Program, or LAMP, is a $5.5 billion capital investment project reshaping ground transportation access to LAX. Its core components are designed to eliminate decades of congestion by reconfiguring how passengers arrive at and depart from one of the busiest airports in the world. At the center of the program is the 2.25-mile automated people mover, an elevated train system that will connect terminals to new off-site facilities. By 2026, all 6 stations of the APM are in advanced phases of construction. Guideway installation is complete, and systems integration is actively underway. This includes communications, train control, traction power, and platform screen doors. Testing of the first train sets began in 2024, and full pre-revenue operations are scheduled for mid-2026, with the line expected to open to the public later in the year. The APM will operate 24 hours a day, with peak headways of under 3 minutes, linking the central terminal area with 3 major intermodal access points: the Consolidated Rent-A-Car Facility, the Intermodal Transportation Facility, West, and the future Airport Metro Connector Station at 96th Street. These access points are critical to shifting passenger movement away from curbside traffic. Construction of the Conrack facility is substantially complete in 2026. Located east of the 405 freeway, this 5.3 million square foot structure consolidates over 20 rental car operations into a single vertical facility, reducing shuttle trips by over 3,000 daily. The facility includes ready return areas, maintenance bays, fueling stations, and direct access to the APM. Operational turnover to rental car companies began in late 2025, with phased occupancy continuing through 2026. The ITF West, a major drop-off and pickup location with public parking, opened in 2021, but continues to evolve in 2026 with integration of pedestrian pathways, wayfinding systems, and last-mile transit connections. The facility includes nearly 4,300 parking spaces and serves as the western terminus of the APM. It also supports the broader mobility plan by acting as a ground transportation hub with connections to shuttles, rideshare services, and regional buses. On the eastern side of the system, construction of the Airport Metro Connector Station, led by LA Metro, is active in 2026. This facility will link the APM to the regional rail network via the Metro K line and future expansions. Platform structure, track installation, and system integration are progressing, with projected completion targeted for 2027. When operational, it will allow passengers to reach LAX from the metro system without the need for a vehicle. Additional work in 2026 includes extensive roadway realignment within the central terminal area. This involves upgrading access roads, curbs, and signage to match the new passenger circulation model, including drop-off lanes designed for rapid movement to the APM platforms. Pedestrian bridges linking terminals to the APM stations are in final construction stages, involving glass installation, elevator commissioning, and ADA compliance checks. The LAMP project also integrates sustainability features. Solar panels, electric, vehicle infrastructure, and stormwater capture systems are being commissioned across multiple facilities. The APM itself is all electric, designed to reduce greenhouse gas emissions by over 30,000 metric tons annually once fully operational. Hidden behind its historic Beaux-Arts facade, Chicago Union Station is undergoing a long-term transformation that positions it among the city's most complex and consequential megaprojects. Rather than a single construction effort, the Union Station redevelopment is a layered program of renovations, expansions, and adjacent real estate projects designed to modernize a century-old transportation hub while it continues to serve hundreds of thousands of daily passengers. Union Station originally opened in 1925 and was designed for an era when long-distance rail travel dominated intercity transportation. Over time, train volumes declined while commuter traffic surged, leaving the station undersized for peak demand and outdated in its circulation, safety systems, and passenger amenities. By the early 21st century, deferred maintenance and congestion had become systemic problems, prompting a phased redevelopment strategy rather than a full shutdown reconstruction. Early modernization work began in the 2010s with targeted interior renovations. These included structural repairs, roof restoration, upgraded electrical and mechanical systems, and improvements to life safety infrastructure. The iconic Great Hall underwent a major restoration completed in the late 2010s, addressing water infiltration, damaged stonework, and aging lighting systems while preserving historic architectural elements. A key milestone in the redevelopment timeline was the reopening of the Chicago River entrance on the station's west side. This new access point, completed in the early 2020s, created a direct pedestrian connection between Union Station and the Riverwalk. Construction required excavation, floodproofing, and the installation of new vertical circulation systems, all while maintaining rail operations below. Passenger circulation improvements have been central to the project. New corridors, widened passageways, and reconfigured waiting areas have been built incrementally to reduce bottlenecks during rush hours. These changes are designed to accommodate future ridership growth driven by increased metro service and potential intercity rail expansion. Beyond the station itself, the redevelopment includes major overbuild and adjacent construction projects that rely on Union Station's air rights. The most prominent is the Union Station Tower development on the south side of the station. Construction of this high-rise office tower began in the early 2020s and required building directly over active rail tracks. This involved the installation of massive transfer girders, vibration isolation systems, and precisely sequenced foundation work to avoid disrupting train service. Additional overbuild phases are planned for the north side of the station, with long-term proposals envisioning multiple towers constructed above rail infrastructure. These future phases remain dependent on market demand and financing, but are entitled under the broader redevelopment framework. If fully built out, the overbuild components would add millions of square feet of office and mixed-use space above one of the busiest rail terminals in the country. Transit infrastructure upgrades are another major element. Platforms and track-level systems have been incrementally improved, including drainage upgrades, platform edge repairs, and signal coordination work. These projects are often executed overnight or during limited service windows, extending timelines but allowing continuous operation. From a construction sequencing perspective, Union Station's redevelopment is uniquely constrained. All work must be phased around active Amtrak and Metra service, limiting the size of work zones and requiring extensive temporary supports. This has stretched what might otherwise be a decade-long rebuild into a multi-decade mega project. Covering more than 27 acres across multiple downtown blocks, Miami World Center is not a single construction project, but a layered mega project built through coordinated phases that collectively reshaped the northern edge of downtown Miami. Miami World Center is located north of the Central Business District, bounded generally by Northeast 2nd Avenue, Interstate 395, and Northeast 8th Street. The site consisted for decades of underutilized parcels, surface parking, and fragmented low-rise structures. Formal planning for redevelopment began in the early 2000s, with land assembly occurring gradually over many years. The scale of the site required a master-planned approach rather than a single build execution. Major construction activity began in the mid-2010s, following zoning approvals and infrastructure agreements with the City of Miami and Miami-Dade County. Early phases focused on horizontal construction, including demolition, mass grading, utility relocation, and the installation of new underground infrastructure. Water, sewer, power, communications, and stormwater systems were rebuilt to support millions of square feet of future development. A defining construction element of Miami World Center was its internal street grid. New public streets were carved through the site, requiring roadway construction, drainage systems, sidewalks, lighting, and streetscape elements. These streets were designed to function as permanent city infrastructure rather than private access roads, integrating the development into the surrounding urban fabric. Vertical construction followed in multiple, overlapping phases. Residential towers were among the first major structures to rise, each requiring deep foundations suited to Miami's limestone geology and high groundwater conditions. Pile foundations, reinforced concrete cores, and high-rise flat-plate floor systems were used across most towers, with construction sequenced to allow simultaneous builds on adjacent parcels. Retail and commercial structures were developed at the podium and street levels. These buildings required large-span structural systems to create flexible interior layouts for tenants. Mechanical and electrical systems were distributed through shared service corridors to reduce redundancy across the district. Loading docks and service access points were consolidated to minimize street-level disruption. One of the most significant infrastructure integrations within Miami World Center was its relationship with regional transit. The development was designed around proximity to Brightline's Miami Central Station, as well as Metro Rail, Metro Mover, and bus connections. Pedestrian corridors and public spaces were constructed to funnel foot traffic between transit nodes and interior blocks, requiring careful grading and structural decking over below-grade utilities. Construction timelines varied by parcel. Early residential and retail components began delivering units around 2018 and 2019. Additional towers and commercial buildings were completed in the early 2020s, with construction continuing in phases as market conditions and financing allowed. Unlike a single mega project with a fixed end date, Miami World Center evolved through staggered completions. Hotel construction formed another major component. Large hospitality structures required distinct structural and mechanical systems, including back-of-house service cores, conference spaces, and rooftop amenities. These buildings were constructed concurrently with residential towers, increasing logistical complexity across the site. Parking infrastructure was largely integrated into podiums and below-grade levels. This required excavation, dewatering, and reinforced slab construction beneath active building sites. Parking systems were designed to serve multiple uses, including residential, retail, and event traffic, reducing the need for standalone garages. From a construction management perspective, Miami World Center required coordination across dozens of contractors, architects, and engineers. Crane operations, concrete pours, and material deliveries were scheduled to avoid conflicts within a dense, active site. Safety planning was critical due to the proximity of Interstate 395 and ongoing city traffic. The megaproject also included public space construction, such as plazas and pedestrian promenades. These areas required structural support for landscaping, irrigation systems, and integrated lighting. Public realm construction often occurred late in each phase, following heavy structural work.
The G Line, formerly known as the Orange Line, was never designed to stay the same. From the beginning, it was a workaround, a bus rapid transit route built in place of a rail line due to funding constraints and political compromise. But over time, its ridership and strategic location forced the city to rethink what it could be. Now the G Line is undergoing a major transformation, an infrastructure upgrade project spanning the entire 18-mile corridor through the San Fernando Valley, pushing the limits of what bus transit can do in Los Angeles. The goal is simple: increase speed, capacity, and safety. But executing that goal has required deep and complex engineering interventions at nearly every point along the route. One of the most critical changes is the installation of a state-of-the-art signal priority and preemption system. Unlike traditional traffic signals that respond to fixed timers or limited sensors, this system actively clears intersections ahead of approaching buses, reducing delays and allowing for smoother flow across dozens of street crossings. Another major element is the construction of grade separations, rail-style overpasses and underpasses at the busiest and most delay-prone intersections. Key locations like Sepulveda Boulevard, Van Nuys, and others are being excavated and rebuilt with concrete bridges and undercrossings to allow buses to pass through without ever stopping for cross-traffic. These structures require complex retaining wall systems, traffic rerouting, and in some cases, full reconstruction of local street infrastructure around the new grades. To support higher frequency service, the corridor is being outfitted with new power systems, bus-only lanes resurfaced with heavy-duty concrete capable of supporting constant vehicle weight, and upgraded station platforms. The existing asphalt guideway, originally built to mimic light rail tracks in layout, has been deteriorating under the strain of articulated buses. Rebuilding it requires full-depth removal and replacement with reinforced concrete slabs, tied into a subsurface drainage system to prevent water intrusion and pavement shifting over time. Platform upgrades go beyond aesthetics. Stations are being lengthened to accommodate longer, higher-capacity buses and future electric models. Each platform is being raised and re-leveled to allow for near-zero gap boarding, speeding up passenger flow and improving accessibility. Integrated electrical conduits and utility vaults are also being installed during construction to prepare for future overhead charging systems as the fleet transitions to full electric. A core part of the upgrade involves upgrading the actual vehicle fleet. Metro is phasing in battery electric buses with larger passenger capacities, regenerative braking systems, and onboard diagnostics. These buses weigh more than their natural gas predecessors, which has direct implications for bridge loading, braking distances, and pavement wear. Engineers had to revisit structural tolerances across the entire corridor, from culverts and embankments to turning radii and clearance zones, to ensure long-term durability under heavier rolling stock. Fiber optic lines are also being laid alongside the corridor to support real-time monitoring. Everything from vehicle location, signal interaction, passenger load, and environmental data will be fed into Metro's central control center. This data will be used not just for dispatch, but to dynamically adjust signal cycles and reroute in case of emergencies. Drainage systems along the G Line were never built for current-day storms. As part of the upgrade, culverts are being expanded, bioswales are being added to medians, and runoff channels are being lined with concrete and fitted with sensors to monitor flow levels during heavy rain. All of this is necessary to prevent trackway flooding and preserve the subgrade from erosion. In 2026, right in the heart of San Francisco's Soma district, the 5M project stands as one of the city's most active megaprojects under construction. This mixed-use development is bringing new energy and density to the blocks surrounding Mission, 5th, and Howard Streets. Long a patchwork of surface lots and low-rise structures, designed to create a live work-play ecosystem in the center of downtown. The 5M project is pushing forward this year with the final phases of its build-out, aiming for full completion by 2027. The core of the project is a multi-building, multi-acre redevelopment that includes housing, office space, community facilities, and public plazas. As of 2026, the residential component is nearing its final stages, with interiors being completed, amenity spaces outfitted, and streetscape work wrapping up. One of the tallest residential towers in the project, now visibly finished on the exterior, is expected to open its doors by early 2027, offering a mix of market rate and affordable units, over 300 in total. The office and commercial buildings that anchor the project are also active hubs of construction. Fit-outs are progressing in multiple towers, preparing space for tech, nonprofit, and creative sector tenants. In 2026, these buildings are expected to start welcoming their first occupants by the end of the year, with full occupancy likely achieved in 2027. It's part of a broader shift in the area, as Soma continues to re-establish itself not just as a tech district, but as a vibrant, mixed-use downtown core. What sets 5M apart in the landscape of San Francisco's 2026 megaprojects is its emphasis on integration with the community. More than just a real estate development, the project was designed to create active public space and cultural infrastructure. At the center of the site, the 5M Park, currently under construction, is being landscaped with flexible gathering areas, art installations, and play zones for families. This green space is scheduled to open alongside the residential buildings in mid-2027 and is expected to become a crucial urban amenity for residents, workers, and visitors alike. This year, the construction crews are focused not only on completing vertical structures, but also on activating the ground plane. Sidewalks are being widened, bike infrastructure is going in, and retail storefronts are being prepped for future cafes, shops, and local businesses. The aim in 2026 is to finish creating a neighborhood that doesn't shut down after office hours, a place where people live, work, eat, and gather 7 days a week. One of the most significant elements under construction now is the dedicated nonprofit office hub and art space, which will house multiple local organizations and creative initiatives. This facility is central to the 5M vision, supporting equity, inclusion, and community-based growth in a rapidly evolving part of the city. Completion is on track for late 2026, with programming expected to launch shortly after. From a development standpoint, the 5M project is compact compared to some of the sprawling waterfront megaprojects elsewhere in San Francisco. But in 2026, it punches far above its weight in terms of impact. Located just blocks from Powell Street BART and Muni lines, its density and transit connectivity make it a model of sustainable urban development, and its blend of housing, employment, and civic use is already influencing how other central city projects are being designed.
In 2026, one of California's most vital water infrastructure projects is under full-scale construction in the western Sacramento Valley. The site's Reservoir project, located northwest of Sacramento near the community of Maxwell in Colusa County, is a planned off-stream reservoir with a total capacity of up to 1.5 million acre-feet. Unlike traditional on-stream reservoirs, sites will store water diverted from the Sacramento River during high flow periods, reducing flood risk while creating a critical reserve for drought resilience. The project entered its primary construction phase in 2026, following final approvals, funding commitments, and site preparation work completed in preceding years. Grading, excavation, and embankment work are active across multiple fronts, including the main site's dam and Golden Gate Dam, both of which will form the eastern and western boundaries of the reservoir basin. These earthen embankment dams will rise approximately 310 feet above the valley floor and span over 4,000 feet in length, designed to safely contain the seasonal floodwaters diverted via a complex network of conveyance infrastructure. Construction of the associated intake facilities on the Sacramento River near the existing Red Bluff and Colusa Basin regions is also progressing in 2026. These facilities will include fish screens, pumping stations, and underground pipelines designed to divert excess winter and spring flows into the reservoir while maintaining compliance with environmental flow standards. Twin conveyance pipelines, approximately 14 miles long, are being installed to transport the diverted water westward to the reservoir basin. At the same time, work is advancing on the terminal regulating reservoir, located near Dunnigan, which will play a role in distributing stored water to the existing Central Valley Project and State Water Project networks. This integration allows site's reservoir to serve multiple uses: agricultural irrigation, urban supply, wildlife refuges, and ecosystem support, particularly in dry years when water deliveries are traditionally curtailed. The reservoir's location was selected in part due to its off-stream design, which minimizes disruption to fish migration and river ecology while allowing water storage flexibility. In 2026, foundation treatment, compaction, and embankment fill placement are underway, utilizing local materials sourced from adjacent borough sites. The volume of material movement is extensive, with millions of cubic yards being relocated and compacted to form the primary dam structures. Concrete structures, including control towers, outlet works, and spillways, are also in early stages of placement. The site's project authority, which oversees the project, expects major civil works to continue through at least 2029. By then, reservoir impoundment and system testing will begin. Full operational readiness is projected for the early 2030s, although water deliveries could begin earlier depending on hydrological conditions and infrastructure completion rates. The construction effort in 2026 employs hundreds of workers and involves coordination with federal, state, and regional water agencies. Lincoln Yards was approved as a planned development by the City of Chicago in 2019. The approval framework allows for up to approximately 14 million square feet of total development, making it one of the largest private real estate projects ever approved in the city. The master plan includes high-rise residential towers, office buildings, life sciences facilities, retail space, hotels, and cultural venues, with development spread across multiple phases projected to span more than a decade. A critical component of the project is its infrastructure construction, much of which must be completed before vertical development can occur. Planned infrastructure work includes new internal road networks, utility corridors, riverwalk expansions, and flood mitigation systems. One of the most significant infrastructure elements is the proposed extension and redesign of arterial roadways to connect the site more effectively to surrounding neighborhoods and regional transportation networks. Transit has been a central planning issue for Lincoln Yards. The original approval included provisions for a new CTA rail station on the Red Line, intended to support future density. While the station is not yet funded or scheduled for construction, planning and right-of-way considerations were integrated into the site layout. Interim transportation strategies rely on bus service enhancements, bike infrastructure, and pedestrian connections. Vertical construction was initially anticipated to begin in the early 2020s, with early phase buildings focused on office and life sciences users near the river. However, shifting market conditions, financing challenges, and changes in office demand delayed large-scale building starts. As a result, much of the project remains in a pre-vertical construction phase, with focus placed on land preparation and long-term infrastructure planning rather than skyline-defining structures. Environmental and flood resilience construction plays a major role in the project's scope. Portions of the site lie within a floodplain, requiring elevated building pads, stormwater detention systems, and reinforced river edges. These systems are designed to meet modern floodplain management standards and reduce pressure on Chicago's combined sewer system. The full build-out timeline for Lincoln Yards has always been long-term. Even under original projections, completion was expected to occur in phases extending into the 2030s. Current expectations continue to place full development well into the next decade, with construction activity expected to ramp up incrementally rather than all at once. This phased approach allows the project to adapt to economic conditions while maintaining entitlement approvals. In the broader context of Chicago's megaprojects, Lincoln Yards differs from infrastructure-driven efforts like airport expansions or flood control systems. Its scale comes from land area, development rights, and long-term transformation rather than a single signature structure. If completed as approved, it would introduce tens of thousands of residents and workers to a formerly industrial zone, reshaping the North Branch corridor. Set within the dense fabric of downtown Miami, Miami Central represents one of the most complex, privately delivered megaprojects ever completed in the city, combining rail infrastructure, vertical construction, and urban redevelopment into a single coordinated build. Miami Central is a mixed-use, transit-oriented development centered on the southern terminus of Brightline's intercity rail system. The project occupies multiple city blocks between Northwest 1st Avenue and Northwest 6th Street, directly adjacent to Government Center. Planning for Miami Central began in the early 2010s as part of a broader effort to reintroduce intercity passenger rail to Florida, while simultaneously redeveloping underutilized downtown land. Construction officially began around 2014, with early work focused on site preparation, demolition of existing low-rise structures, utility relocation, and rail corridor reconstruction. The project required rebuilding active rail alignments while maintaining freight operations on the Florida East Coast Railway, necessitating phased construction sequencing and temporary track realignments. At the core of Miami Central is the Brightline station, constructed as an elevated rail terminal spanning multiple blocks. The station structure required long-span concrete and steel framing to support train platforms above street level while allowing uninterrupted traffic flow beneath. Platform construction included high-load track slabs, vibration mitigation systems, signaling infrastructure, and integrated safety systems compliant with federal rail standards. Below and around the station, the project incorporated significant structural podium construction. Large transfer slabs were built to distribute loads from residential towers above while accommodating open concourses, retail space, and passenger circulation areas below. This approach allowed rail, pedestrian, and vehicular systems to coexist within a constrained urban footprint. Miami Central includes multiple high-rise towers developed in phases. The first residential towers began vertical construction after the station structure was well underway. These towers required deep foundations and auger-cast piles to manage Miami's soil conditions and groundwater levels. Structural systems used reinforced concrete cores with flat plate floor construction, optimized for residential occupancy and high-rise efficiency. In addition to residential units, Miami Central incorporated office space, hotel components, and retail frontage. Mechanical, electrical, and plumbing systems were designed to operate independently across uses while sharing centralized infrastructure where possible. Loading docks, service corridors, and back-of-house systems were embedded into the lower levels to minimize surface disruption. A defining construction challenge was integrating multiple transportation modes into a single site. Miami Central connects Brightline Intercity Rail, Metro Rail, Metro Mover, Metro Bus, and pedestrian networks. Construction included new elevated walkways, platform connections, fare control zones, and vertical circulation systems, linking existing transit infrastructure to newly built spaces. Roadway reconstruction was another major component. Portions of Northwest First Avenue and surrounding streets were rebuilt to accommodate new traffic patterns, curbside loading, and pedestrian access. Streetscape improvements included drainage upgrades, structural decking over rail corridors, and reinforced pavement designed for heavy service vehicles. The timeline of Miami Central unfolded in stages. Rail corridor and station construction progressed between roughly 2014 and 2017. The Brightline station reached functional completion in late 2017, coinciding with the launch of passenger service between Miami and Fort Lauderdale, later extended to West Palm Beach. Full station operations began in early 2018. Residential towers were delivered in phases, with initial buildings completed around 2018 and additional towers finishing in subsequent years. Retail and public spaces opened gradually as tenant build-outs were completed. The project did not conclude with a single completion date, but by the late 2010s, Miami Central was fully operational as a transit hub and mixed-use district. Within the context of Miami's biggest megaprojects, Miami Central stands out for being privately financed and rail-centric. Unlike publicly led infrastructure efforts such as the Port of Miami Tunnel or airport expansions, Miami Central combined transportation infrastructure with real estate development under a single master plan. This approach shifted how large-scale projects could be delivered in Miami's urban core. From a construction management perspective, Miami Central required coordination among rail engineers, vertical construction contractors, transit agencies, and city departments. Work occurred simultaneously above, below, and alongside active transit lines, requiring constant monitoring of settlement, vibration, and structural movement.